distinguished invitees and alumni, ladies and gentlemen. A warm welcome to you all to what we hope as an important new fixture on the university calendar, as well as for the esteemed individuals representing their companies, corporations, and institutions here today. The Materials Engineering Symposium on Innovations for Industry, or MESI, was conceptualized as an event where prospective employers and interested academia could witness the research work of undergraduates so that they may better understand the focus on innovation and how those work could ultimately contribute to varying interests on the industry. We hope that you will find the event accomplishes all that and more in the coming hours. Also, we believe the conclusion of this session will tie the bonds between the department, its undergraduates, and yourselves. Before anything else, why don't we have a look at the session inauguration video where you will be more convinced about the department and its capabilities.
Humans discovered technology to make people's lives convenient, safer, and sustainable. It has revolutionized the world and continues to change people's daily lives at every second. Winning the technological consumer has become the primary goal of modern-day engineering. As engineering theories progress, it has become overwhelmingly clear that it is the materials that hold the key to the future of engineering. The University of Moratuwa, being the most prestigious and the most sought-after technological university in Sri Lanka, took the initiative to establish this trend-setting interdisciplinary academic field, linking Sri Lankan engineering education with the technology innovators of the world. The Department of Materials Science and Engineering of the University of Moratuwa is the pioneering academic institution in Sri Lanka that provides world-class research and knowledge-driven expertise in the field. The department has a future-oriented mission of becoming a center of excellence in materials science and engineering, with a highly qualified and dynamic group of academic and technical staff. The department is dedicated to produce competitive experts to the industry.
The history of our department spans over 45 years now. In the past 45 years, we have produced more than 1,000 graduates who are employed all over the world. Some are working as engineers, some are working as researchers, some are scientists, and many others working as managers as well. Our department conducts a 4-year engineering degree program in material science and engineering, which has obtained Washington Accord accreditation. This accreditation recognizes our degree, which facilitates the students to be recognized all over the world.
The department conducts an internationally accredited bachelor's degree program in engineering and high-quality research-oriented postgraduate programs of master's and doctoral degree level. It also offers expert solutions and consultancy to both the public and private sectors, contributing to the advancement of the national technological strength. The high-quality degree programs ensure that the graduates are highly capable of exceptionally contributing to the next level of industrial development, especially in the areas of material design, product design and manufacturing, process optimization, and quality control.
We employ materials engineers in 3 major sections in our operations. One is the product R&D and product development, where the materials and development of new, looking for new materials and the combinations of those that improve the performance of our products. Then we have the in-process materials and manufacturing process, where the various material engineers have various roles to support us in that. And then we have the material testing and quality control. So all the incoming materials we need to test, we need to validate, we need to work with our suppliers on developing the best possible materials that go into our products.
The primary reason why the graduates of the department are highly sought after for specific purposes is the comprehensive curriculum offered with professional practice. While the basic concepts and principles are introduced in the first 2 academic years, in-depth knowledge and practical training is given with regard to engineering materials such as polymers, metals, glasses, ceramics, and composites, etc. from the 3rd year. The student-centered learning environment ensures that the students are well equipped with exceptional knowledge as well as practical training needed. The undergraduate program is carefully designed in consultation with all stakeholders through the Department Industry Consultative Board in such a way that the students are provided with the expertise necessary to become the model changers at the next level of the local and global industrial development.
Material science and engineering provide us with a platform to study and understand the materials not only at macroscopic level but to microscopic or nano or even to atomic levels.
During my school days, I had a dream of becoming a scientist one day. I was inspired by gazing upon great scientists and their great work. So when it came to my field selection, it was quite obscure because I wanted to do something that I would love doing for the rest of my life. Then I was first introduced to the Department of Material Science and Engineering, and I knew this was going to be my first choice of preference because this undergraduate program is quite capable of exposing you into interesting fields like electronic materials, nanotechnology and biomaterials, and many more which are leading the global technological advancement.
In the final year, the students conduct a high-quality and pragmatic research project, demonstrating how they intend to address real-life problems in the industry or professional research. The department also holds the annual Research Symposium on Materials Engineering Innovations for Industry to showcase latest research work.
For my final year research, I chose to make titanium dioxide nanotubes, and we are trying to manipulate the properties of these nanotubes by changing the process parameters. And these nanotubes can be used in a wide range of applications, ranging from biomedical applications, sensors, supercapacitors, and also solar cells.
For my final year project, I've chosen a project collaboration with industry, where I worked on a project to enhance the solubility of nichrome alloy. We have chosen a material to enhance the solubility on nichrome alloy. So we are extremely excited about what we are able to do by this technology and these types of material processing.
The department offers a comprehensive range of postgraduate study opportunities, from coursework-based programs for master's degree in material science and master's degree in nanotechnology to research-based degrees in Master of Philosophy and Doctor of Philosophy.
We work with a wide variety of materials like semiconductors, graphene, carbon nanoparticles, and different treatment methods as well. That's why I felt the need of understanding in depth about these materials, how they behave, and why they have a unique behavioral method. I think that's what made me to follow this master's program at Material Science and Engineering Department.
The department has the best combination of advanced laboratory facilities and personal expertise in Sri Lanka in the field. The full benefit of the wide range of equipment is provided for experimental facilities to students and for research and industrial services. Equipped with exceptional technical skills, interpersonal skills, and also the industry exposure, the graduates from the department thrive in their professional careers with a wide range of opportunities open for them, from conventional manufacturing and services to modern high-tech industries.
We always look one cycle ahead, meaning that we want to be one step ahead of the competition. So that means we need new knowledge. So I think the materials engineers who are coming from the department has to bring, in fact bringing new knowledge required for this particular the aspect. So today they engage in different functions like say the product design, controlling the product, quality assurance, and also they play their roles at different capacities in the company, like say as the junior engineers, senior engineers, managers, and also some of them are working in the strategic level, like the executive director category.
The Department of Materials Science and Engineering thus offers a unique opportunity for the enterprising young undergraduate to build a solid foundation for an engineering career with a promising future to become a creator of creation who can harness all worldly resources for the betterment of mankind.
I hope you all enjoyed the video. To start the proceedings and welcome you formally, let me invite the gentleman who has gone great lengths to coordinate and organize this event, Dr. AAG Arvinda Begunawardana. Sir, the floor is yours.
Thank you, Vinuri, for the introduction. Distinguished guests, it is with great pleasure to welcome you to our 4th annual event, Materials Engineering Symposium on Innovations for Industry 2021, with the Association of Society of Material Science and Engineering, SOMS. So as the program chair for the second consecutive time and the final year undergraduate project coordinator, I strongly believe this symposium actually will provide an enhanced outlook of the research activity that we carry out in the Department of Materials Science and Engineering. Initially, the materials science and engineering is a well-distinguished area in many developed countries, as it is the core field in both design and manufacturing. The Department of Materials Science and Engineering is the only national institution currently catering to this demand in the aspect of education as well as in the materials research in Sri Lanka. The symposium this year is to be hosted through an online platform due to prevailing pandemic conditions around the world. Hosting a symposium in online form is always challenging, but it is we have to do it anyway. But there is no hesitation that pandemic has hit the progress of many research activities carried out in the Department of Materials Science and Engineering at undergraduate as well as postgraduate level. The reason is generally the nature of work carried out in the department is mainly lean on laboratory facilities. Though with the situation, what we all facing, mainly due to difficulty in accessing laboratories, most of the objectives of the original research proposals have had to evolve towards modeling and simulation aspects. So the symposium theme is actually changed to innovative materials through mathematical modeling and simulation, as on par with the current circumstances. In parallel with the technical session, we host a short workshop for the 3rd time on the theme of recognizing the rewarding trends in engineering for advanced level school students who study in the physical science stream. I strongly believe as the program chair that this event will be effective to you in gathering new knowledge in materials world and as industrialists to collaborate with us to advance for the betterment of your organization and ultimately Sri Lanka. I take this opportunity to thank everyone who helped and supported to make this symbolic online event a success and hope the time spent in MESI 2021 is worthwhile and exciting. So as the program chair, I hope you will continue to support future MESI events for the betterment of every aspect, and let's hope we all can spend an exciting time in person in coming MESI events. Thank you. Over to you, Tony.
Thank you, sir. The challenges before an individual who heads a department of any institutions are countless. This is especially true for the academic departments of Faculty of Engineering at University of Moratuwa. With that in mind, let me welcome the gentleman who has become the beacon that guides our department to strive for greater standards. The the department, Mr. V. Sivahar. Sir, the stage is yours.
Thank you, Henry. And good morning, everyone who has joined online. So I will not be seeing your faces, unfortunately, but situation demands that. So on behalf of the Department of Material Science and Engineering, I welcome everyone who has joined online with the MESI 2021. So as Dr. Aravinda mentioned, this event is now being organized for the 4th year, jointly by the department and Society of Materials Engineering students. So the first symposium was held in the year 2018, right, as an initiative from one of our young lecturers, Dr. Mrs. Galhenage. And now this is the 4th year, as I and Dr. Aravinda mentioned. It has now become an important annual event of the calendar of the department. Last 3 years, as we all know, this symposium was held within the department premises. But however, this year we were forced to go online to make sure that to make sure the health and safety of everyone who participates. So the symposium actually was originated with the aim of showcasing the research activities of the department to the university students as well as to the industry. Also, another focus of this event to increase the department industry interactions, right, on the domain of the research. Later, as Dr. Aravinda mentioned, the scope has been expanded towards focusing with GCE advanced level students, right, who will be the potential stakeholders of the department. And this event, right, create awareness among those A-level students about the field of material science and engineering and the research activities of the department. Of course, if you look at any research happening all over the world, it can be based on any discipline, but final focus will be on the development of a material, right? So basically every research at the moment going on, right, you can see it may be from different disciplines, but the main focus is innovative materials. The theme of this year's MESI is innovative materials through mathematical modeling and simulations, right? This reflects the current trends with the adoption of the new normal. I take this opportunity to thank all the students and the staff who worked towards organizing this virtual event under these difficult circumstances, especially Dr. Aravinda Abhegunawardana. And finally, I wish all the success for the event, and I wish all the presenters, right, and all others who have joined, especially I think the new intake of semester 1 students have joined with us. So they will also benefit, right, from this symposium. So they will get a chance to see what material science and engineering is and what type of research we are doing in the department. Wish you all the best. Stay safe and healthy. Thank you all.
Thank you very much, sir. The supervision of 12 departments of infinitely diverse subject areas under the banner of engineering is quite a difficult task. However, he has taken this hard job with admirable ease. Please welcome Dean of Faculty of Engineering, Professor Nalin Wickramarachchi. Over to you, sir.
So, the head of department of Material Science and Engineering, Mr. Sivaha, the program chair, Dr. Aravind Abegunawardena, dear professors and colleagues in the Department of Material Science and Engineering, and distinguished guests, dear students. First of all, let me congratulate the department for organizing this symposium, even if the conditions are not ideal. The last 3 years, of course, we had the symposium physically at the university, but due to the adverse conditions worldwide, today, of course, you have organized this as a virtual event. But still, it's a great effort. So I want to thank you, everyone in the department, for organizing it despite the adverse conditions, together with the organizers and also Society of Materials Engineering. When it comes to materials engineering, of course, we all know that materials are the bread and butter of engineering. It used to be that a few decades ago, the main consumer of materials engineering was traditionally civil engineering and mechanical engineering for their structural designs, as well as mechanical engineering for manufacture and design. But today, of course, situation has changed drastically. Material engineering, although not visible, I guess the biggest consumer of materials in engineering is semiconductor industry. Now, this is not something that is easily visible because most of the semiconductors that we consume are inside machines and they are not easily visible. But the advances in materials engineering were extremely important and continue to play a very important role in advanced semiconductor materials that we use in our everyday lives. Even this virtual conference symposium is made possible by the advances of IT, which of course fundamentally depends on the advances in semiconductor materials. Also, recently, of course, the materials engineering has gone beyond that. We can see that our scope of engineering, materials engineering, has expanded drastically, because as the theme of this symposium tells us, the innovative materials through mathematical modeling and simulations. Of course, we know that there are new areas coming up in materials. There are functional materials. Of course, the structural and metallurgy was the foundation, but from now on, things like materials in functional materials, green technologies, materials for green technologies, energy and environment, and also biotechnology. So those are areas where material engineering is more and more involved these days. So in that scenario, I am really happy to see your thematic areas of functional materials, green materials, and energy and environment as part of the thematic areas of this symposium. And also, I must mention that as a faculty of engineering, we have been promoting research for several reasons. Research is not just for the sake of research. We know that industry is always looking for new innovative materials, innovative processes, innovative productions, and so on. And the innovation does not come automatically. It's something that students learn by practice. So that is where research is important, not just for postgraduate students, but for undergraduate students as well. Without research, of course, students will not gain innovative approaches, innovative thinking that they are expected to perform when they go to the industry. So one aspect of this kind of research symposiums is basically to let the students know the innovative approaches of their colleagues that help both to advance the materials engineering and as well as for the advancement of the industry. But that is, innovativeness is only one aspect. There are other aspects to research. The next one is, of course, knowledge dissemination. As a university and as a faculty of the most prominent engineering faculty in this country, knowledge dissemination has become one of the most important functions of engineering faculty today. Of course, I am very humbly proud to mention at this forum that whenever some critical technological problem occurs in this country, I will always get a call or a letter from officials who are responsible to name an expert to see how the problem can be resolved or what the problem was in the first place. We get enormous number of such requests asking for help of our own experts to resolve many problems that are many issues, technical issues that are facing the nation today. One of such example is the current crisis, which is still going on about the gas issue. Many of our experts are directly involved in the investigation of that. But that is only one example. Just about every professor in our engineering faculty are involved in one or the other investigations that are real issues in the country. So in a way, I am happy that expertise that is in our faculty, in our university, is sought after very much by the industry and the government in this country. But at the same time, that expertise does not come simply by the textbook knowledge. And that expertise comes from not just by repetitive experience either. We have to keep doing our research. We have to keep innovating. We have to keep creating new knowledge. So that is why this kind of symposiums are important. While they tell the students, prospective students, what to expect, and at the same time, it tells the industry what we are doing here and what our future goals are and what kind of new knowledge that we are creating. So those have been our major goals in the engineering faculty. And then, of course, one of the fundamental goals of the engineering faculty is to create not job seekers, but job creators. And of course, everybody cannot start their own industry. But through innovativeness, there will be a change in the thinking of the students, that they must be able to, at least some of them must be able to create their own industries, their own businesses. That is what we hope for, this kind of innovative approach to engineering. So I'm confident that the Materials Engineering Symposium, which you are organizing for the 4th time, will be a major milestone in achieving those goals. I wish you all the best, the organizers and the participants, and wish you a very productive day ahead in the technical sessions. Hope you will learn about the department, about what kind of research and innovativeness that is going on in the department, and what type of industry department relationship exists, and what kind of job opportunities are there, and what's the future of materials engineering. So thank you very much for your patience. I wish you all the best. Thank you.
Thank you very much, sir, for your insightful words. The next item is from our chief guest for this year. I will cordially invite Dr. Arvind Abegunawardana to introduce our chief guest to the audience.
Thank you, Vinay. Dr. J. Kamaladasa has obtained his primary and secondary education at Nalanda College, Colombo, and is a proud alumni of the Department of Material Science and Engineering, University of Moratuwa. Dr. J. Kamaladasa obtained his PhD in Material Science and Engineering at Carnegie Mellon, Pittsburgh, Pennsylvania, USA. His thesis was on novel electron microscopic techniques to characterize resistive switching behavior in titanium oxide and strontium titanate. He was also influential in developing electron channeling contrast imaging for the purpose of imaging crystal defects. In 2013, he joined Intel as a reliability engineer, Hillsboro, Oregon, USA, and has taken on multiple roles, including acting as a reliability risk owner for electromigration, yield, FI engineer, and test chip program manager. He currently works as a staff reliability engineer specializing in design technology core optimization. So over to you, Dr. J. Kamaladasa.
Good morning, folks. Thank you for inviting me as the chief guest to this MES2 symposium that aims to bridge the gaps between faculty, industry, and students. It's always good to have these kinds of conferences and places where students and industry meet directly, and they have a clear communication with each other on the expectations that they have, what kind of skill sets they're looking for, and things like that. It also helps the faculty to align with the expectations of the industry that we serve. So I am glad to be a part of this, and hopefully you all will have a good conference. I was asked to talk about my experience at Intel, how I use my background in material science to do the day-to-day tasks that I do, and also to give the students some idea of the research or the career path that I took. So I'm going to talk briefly about my PhD research as well. And I'm going to end the talk with a success story that all of you, faculty, students, and industry, might find useful and might find a goal or inspiration to strive towards. So let's get started. I'll go through my background first. I did my BSc in Material Science at UOM in 2009. I then went on to get my PhD at Carnegie Mellon in Pittsburgh in 2013. I'm now working as a staff REL engineer at Intel since 2013. What do we do at Intel? We are in the business of transistors, specifically decreasing the number of transistors that we can, or the size of the transistors as much as we can. So we try to pack a lot of transistors in the same space with each technology node. And as you can see, when we started back in 1960s, it was in the hundreds of microns space, and it has slowly decreased to submicron, and we're in the space of sub-nanometer regime where quantum effects like quantum tunneling takes place. So we've done as much as we can to decrease the size of the transistor in a one-dimensional scale. Now we're doing tricks in the two-dimensional and three-dimensional space to even further decrease that size, stack transistors on top of each other, for example, and pack more and more transistors so that people who draw the circuits can gain that improvement from more transistors. So what do we do with these transistors? Well, our core business is in the desktop and laptop CPU market. It has been so for the last 3 or 4 decades, but recently we have expanded our market segments to various things like data center, AR, VR, FPGA, hard drives, SSDs. And so we have changed our company mindset from becoming a CPU-centric company to an XPU-centric company, X as in variable, so it can be a CPU, GPU, FPGAs. The core is we're making computing stuff, and it could be the conventional stuff, but it could be something different, whatever the market requires. So where does material science come in? So before we go to that, let me take a step back and talk you through the computing stack that we have. When people try to create an application or a solution to solve something, say for example, you're optimizing the supply chains of a company, or optimizing the performance of a game, or let's say you're solving the quantum wave equations, right? The applications and solutions that we do with computing can be wide ranged, right? We start with that, and then we figure out a way to solve that problem. That's the algorithm. So we choose what's the way we want to solve it. Is it AI network? Is it a quantum computing algorithm? Is it a classical case of a 2-body problem or a 3-body problem, or like something like that? So we find a path to solve it, and then we use a programming language to code that. So it can be a scientific programming language, like a matrix-based programming language like MATLAB. It can be a data science programming language like R. It can be a classical programming language like C# or C++. So once we figure that out, we compile it to an instruction set so that the machine knows what we're talking about. So those 3 things, at least the first 2 things, fall on the math, computer, and data science. Then we go to the micro architecture of the chip, and that's basically how the computation is done. So you can do the computation in parallel threads. You can go forward in time, and you can predict the future computations of that thread and do that computation proactively so that the computer doesn't waste time until the rest of the computation happens. So things like that fall in the micro architecture of computing. And Intel has its own architecture, it's called Intel Core. AMD has its own architecture, it's called Zen these days. So there are different things to choose from. And then to create that micro architecture, you need components. And these components are usually gates and flip-flops and things like that. And gates, NAND gates and NOR gates and things like that are made out of transistors. So these levels of abstraction, the micro architecture gates and transistors, they fall under electrical engineering. And experts in each of these fields, they are very highly specialized experts. They have their own problems to think about, right? When we are trying to put into market a CPU, all of these things have to be optimized and improved on. But then we come to the basic fundamental block, or how are transistors made, and that's where material science comes in, right? So semiconductors, as you know, are the building block of transistors, and basically they're PN junctions doped like silicon with phosphorus or arsenic. And when you have a PNP junction or an NPN junction, that becomes a transistor, that becomes a switch. So this is where material science comes in. And the reason why I wanted to show you this is that it's very crucial that even material scientists who work on these semiconductors comprehend the whole stack and comprehend the problems that each of the experts have in math, computer science, and electrical engineering. For example, if you can come up with new material science solutions to the problems that the AI people are having, right? You could create a component, a completely new component that could help the whole stack, right? So that's where the power of material science comes from. I'll give you an example, a quite big example actually that happened in the recent few years. So with the computing space has gone from classical computing to AI computing, and the main problem with AI is that it requires a lot of computation, and a single CPU doing all that computation is very inefficient, right? And so if it's possible to move that computation away from the single CPU, like what people have done with GPUs, right? People use GPUs instead of CPUs to do AI computation. So that's one example, but the next example is that if you can move that computation away even further than the GPU, right, that could improve AI quite a bit. And what material scientists have found out was that they could make a component ReRAM in various ways. They stack each other in a crossbar kind of configuration, and they can create matrix multiplications, or they can compute matrix multiplications inside the RAM. So the RAM is very outside the CPU, right? So that creates more efficiency for programming like AI and neural networks. So it's very important that even as material scientists, you understand the problem statements that each of these steps have. All right, so let's go into the brunt of the material science in the semiconductor field. When we make a computer, what are the criterias, or what kind of things do we look for in a material? The first thing, as you might have guessed, is performance. We want our materials to switch fast, right? We want our CPUs to have higher frequency. And then we also want to decrease the timing between the circuits, and that depends on the RC delay. So the resistance and the capacitance, if they increase to an extent where the time that it takes for a signal to go from one circuit to the other decreases, then it does not matter how much fast your transistors can switch, right? So RC delay of materials can also play a huge role. So you need to reduce the capacitance, you need to reduce the resistance. The second major thing that we need to focus on is yield. And this relates into how we actually create these semiconductor chips. We create these in clean room factories, right? So clean rooms are basically spaces where the particle count in the atmosphere is extremely low. So it's in the ppb, parts per billion. And even further down the line, right, we want to decrease it as much as we can. And it's not enough to do that. We also need materials that go into the chip that do not easily interact with the materials outside. It could be the environment outside, or it could also be the tools that are used to make these CPUs. So the thin film deposition, the electron beam lithography, or CMPs, or chemical mechanical polishing, the dry etchers and the wet etchers and things like that. All those things, the materials have to be robust against contamination. So when it comes to material selections, that also plays a huge role. The third and last thing, and also my expertise, is on long-term durability of materials. And this is an interesting topic for material science because it goes on to a lot of fundamentals that we learn as material scientists. And I'll go through some of the failure modes that happen so that you can get an idea of what kind of problems that we face. So the first one is gate oxide breakdown. This happens when the gate of the transistor, which is supposed to be like hafnium oxide or something like that, that completely stops the current from going into the channel. It just acts as a switch. When that breaks down, the switch no longer, well, the switching can happen, but the leakage can cause the circuit to have problems. And this doesn't happen quickly, it happens during a long time, right? So you need to stress it at high temperatures, high voltages, and things like that. And we call it also time-dependent, dielectric breakdown sometimes, because it takes time. And this happens due to defects inside the gate, and we want to decrease those defects as much as we can. The next thing is hot carrier degradation. This happens due to charge trapping, defects like point defects and two-dimensional defects, dislocations and stacking faults. These create the right thermodynamical trap for charges to accumulate, right, and cause various issues inside the semiconductor. So that's a problem. The other one is radiation effects. We have cosmic rays that come from the sky that hit our computers, our CPUs, and that might cause a bit flip. A bit flip is when a bit changes from 0 to 1 or a 1 to 0, and that will throw off all your calculations, right? So we need materials that are susceptible to radiation effects. The next three failure mechanisms are diffusion-based. People who have studied the first year or the second year material science know that diffusion is the flow of material under a concentration gradient. But there's also a flow of material when there is stress. Specifically here, it's electric stress, thermal stress, and mechanical stress. So in these cases, there can be so much material flow that there might be a hole left inside after the circuit has run. So I have some pictures to show you. So this is a electron micrograph of a hole inside a circuit. And you can see all the copper has been taken out through the electromigration. And so this can happen in various ways. Diffusion can happen through the top surface. It can happen through grain boundaries. It can happen through sidewalls. And choosing the various materials that go into all of these components is important. And depending on how the diffusion happens, you might want to know, what path is the easiest path for the diffusion to take, right? And things like that. So as a material scientist, you will learn to design experiments to figure out these things and to decrease the impact of these things to the circuit. The final thing is thermomechanical fatigue. fatigue is a failure mechanism that also happens in the macroscopic scale of things. It's when tensile stresses and compressive like stresses happen over or cycle through a certain period of time, and that causes the material to break. And it can cause, and mostly causes like ductile failure, right? So even if the material is pretty strong, various effects of grain boundary migration and things like that can cause the material to break easily. And we see that in our C4 bumps where the CPU meets the main board. We have these big tin and lead bumps that go through huge fluctuations of temperature. So there's expansion and contraction, and with that expansion and contraction, there's tensile and compressive stresses. So I've gone through all the failure mechanisms. So these things don't happen again in like the moment you turn on the CPU. It happens over weeks and months. So the way we test this is we do accelerated life testing. We increase the temperature, increase the currents, and from the know-how that we have, from the equations that we know, the temperature dependence of the time to failure and the stress dependence of time to failure, we can back calculate the lifetime as if the computer was running at the use condition, which is usually a smaller temperature, smaller stress current, and things like that. All right, so I've explained what I do in a day-to-day basis. So how can you, as students, faculty, or people who are interested in the semiconductor business get into this, or what kind of research would you need to do? I'll go through my PhD thesis. This is obviously you don't need to do research to this extent, but this is the kind of research that you would want to do if you want to dive deeper. So my PhD was on the electrical switching of titanium oxide and strontium titanate. These materials have what's called a resistive switching property, whereby if you apply a voltage, it will change its resistivity from a low resistive state to a high resistive state and vice versa. And so people didn't know what was the cause of this. What's the material property that causes this electrical switch? So I went on and did a few experiments to find this out. And of course, this is the experiment that succeeded. I'm not going to tell you the thousands of experiments that failed. This experiment where I stressed the titanium oxide in a certain way, and we did it inside an electron microscope, we could see defects or networks of dislocations forming and decreasing in size. And we correlated that to the resistive state. So let me show you this video. This increase in this black portion, what you see, and that decrease in that black portion is the increase and decrease of the dislocation density. And we further found out that these networks of dislocations form into phases, what are called McNally phases. So in terms of material science, right? This is an example of a two-dimensional network of defects forming a three-dimensional network of defects or dislocations turning into a phase change and causing a change in the electrical properties, right? So this kind of research into material properties that correlate with the electrical properties, this is a highly impactful area of research and something that you can keep your thoughts on, right? You can't do the same thing, of course, but if you can figure out a way or a reason why materials behave the way they do, and certain properties that we can use in the electronic industry, then you have a good research thesis, right? And it also helps, right, that you know the problems in the semiconductor stack. Like I told you in the previous slide, what kind of problems do the computer scientists face? You know, what are the solutions to those things? What kind of things can material science do, or what kind of components can we make to solve those problems in those spaces? So that's the research that I did. And so I'll leave you with this final words of wisdom. We at UOM know the impact of wisdom, right? And so you all are here in this symposium trying to learn from each other, trying to learn from various parts of your field, how to be a better material scientist. So you already know that wisdom is all wealth. But I want to take that step further, and I want to encourage you to not only stay in your same room or stay in your same school or country, but try to expand your reach further. Because if you go outside Sri Lanka, there are lots of places to learn and grow your skill set. And right now, the world as it is, you can see from this pandemic, the global supply chain also needs to change. We can't just keep on banking on countries like China or Taiwan, right? We need to diversify our global supply chains. Sri Lanka can also contribute to that. But before that happens, we need experts. We need people with expertise to do that. And so to leave you with a success story, I work with these people on a day-to-day basis. These are 10,000 employees in Bangalore and Hyderabad. They constitute the largest campus outside the US. And the way they did this, the way they built their campus is not by waiting for some government to build it for them or some corporation to come into their country and do it for them. They went outside. They came to the US, they did their PhDs or masters, or gained the skill set that they want to gain. And at a certain point, once they reached the critical mass, they went back to their home country. And then they started their own business and then joined Intel. So hopefully this success story leaves you with something to think about. I'm not suggesting that you leave your current job to go somewhere else with this pandemic. Of course, it's even harder, right? But it's something to think about, right? Try not to stay in a box. Try not to stay in the same room that you're in. Try to expand your skill set. So with that, I will leave you folks. Thank you again for choosing me as your chief guest. And hopefully you all will have a good symposium. Thank you.
Informative, mind-blowing and inspiring speech. So to conclude the ceremonial proceedings, we would like to welcome a gentleman who has played many roles on behalf of the Department of Material Science and Engineering. He's very much involved in everything we do, and he always reminds us that there is no limit to the pursuit of knowledge, and he encourages us for it. Please welcome Professor S.U. Adhikari to deliver the vote of thanks. Over to you, sir.
Right, okay. Good morning to all of you. Dean Faculty of Engineering, Program Chair, Dr. Aravinda, Head of the Department, Mr. Sivaha, industry representatives, my fellow staff members, ladies and gentlemen. We have come to the last item of the agenda of the opening ceremony of Materials Engineering Symposium on Innovations for Industry 2021. I have been assigned the task of briefing you the remaining agenda items of the day and to prefer the vote of thanks on behalf of the organizers of this event. Once we conclude the opening ceremony, the technical sessions are scheduled to start, which will showcase the undergraduate research projects. Actually, the first technical session It's supposed to start around 10:30 a.m., but maybe delayed a little while. And the first session will continue until 12 noon, and then we will break for lunch. And the second and final technical session will start around 1 p.m. So if everything goes according to the agenda, we may be able to conclude the MAISY 2021 around 2:30 p.m. In addition to the main agenda, we are running another parallel webinar program, specially designed for school children, basically to introduce and familiarize the field of material science and engineering. So ladies and gentlemen, those are the activity lineup for the rest of the day. So let me conclude the proceeding on the opening ceremony by proposing the word of thanks. First, I'd like to thank Dean Faculty of Engineering, Professor Nalin Kamarachi, heads of departments, directors, and industrial representatives for gracing this occasion despite your busy schedules. Our special thanks should go to the chief guest, Dr. Ray Kamaladasa, staff reliability engineer at Intel USA, who is an alumni of our department. We thank for his excellent presentation on career in material science and engineering. And also, we should thank the 16th batch undergraduate students of material science and engineering who will present their research output at the technical sessions. In addition, we would like to thank the staff of Learn Network for arranging webinar license and other technical support. An activity of this magnitude is not possible without support of our colleagues in the department. Mr. V. Sivaha, our head of the department, Dr. Aravinda Abhigunawardana, the program chair of the Symposium, and all the academic and non-academic staff members of material science and engineering. Thank you very much for your support. Last but not the least, I'd like to thank and acknowledge the effort of our undergraduate students of the department, who are the backbone of this endeavor. Thank you very much. Have a productive day at MAISY 2021. Thank you.
Thank you very much, sir. The theme of the Materials Engineering Symposium on Innovation for Industry 2021 is to explore innovative materials through mathematical modeling and simulations. Thus, let's move on to the technical presentation sessions of the final year undergraduate research projects to witness what our fellow undergraduates have achieved through years of academia. Please welcome Dr. Aravinda Abhigunawardana, Senior Lecturer of the Department of Material Science and Engineering, who will be the session chair for this presentation. Over to you, sir.
Ms. Inuri. In the beginning of this technical session 1, we have actually 5 presentations which has been completed and prepared by our final year undergraduate students with successful completion. And let me go directly to the presentation sessions without wasting more time. So our first presenter is Mr. G.S. Dhananjaya, and the project title is on modeling, synthesizing, and validation of nano-hydroxyapatite formation for medical application. So I will share the screen just to play their presentation, and we have actually a 10 minutes presentation, and if you have any questions to be raised, please feel free. We have additionally roughly 7 minutes to do this Q&A session. So please free to ask questions from these presentations, the presenters, one of the presenters or both of the undergraduates will be, they are available online. So please feel free to ask questions from them.
Hello, welcome everyone. This particular research titled to modeling, synthesizing and validation of nanohydroxyapatite formation for medical application was conducted with my colleague Tumidu Madhusankar under the supervision of Professor Upali Adhikari. Let's move on to our presentation. In the introduction part, actually the hydroxyapatite is a basic mineral component in mammalian heart tissue. Due to its properties like osteoconductivity, bioactivity, and biocompatibility, it is well suited for some medical application. Also, some future trending in medicine like bioceramic coatings, bone fillers, remineralizing agent, especially gene therapy, bone graft substitution, and controlled drug delivery. In the definition of research problem, basically our research problem was how to synthesize pure and nano form of hydroxyapatite and to identify which process parameters are accountable for the particle size of hydroxyapatite, then how to manipulate them in order to have the nano form. Finally, is it possible to build a mathematical relation between process parameters and particle size? Then we set our objectives accordingly with the classical nucleation theory for the nanohydroxyapatite formation. Now, basically, the significance of this study is the purity achieved from biocompatibility. It is done with the wet chemical synthesis method. Then the particle size derived from osteoconductivity. Actually, it is the research in gap because some process parameters which are sensitive to particle size needed to be understood based on some mathematical relations. In the methodology section, first thing was to develop a kinetic model based on classical nucleation theory. Then we design our experimental routine to the wet chemical synthesis method for the formation. Then we statistically validated the kinetic model built. Then we experimentally validated through some analytical instrumentation. Finally, we applied the model built in some nucleation aspects. In the kinetic model development, we derived an expression for the nucleation rate through temperature, interfacial tension, and supersaturation. As you see, our researching relationship was the nucleation rate variation with supersaturation. Supersaturation basically defines how many times the solution is concentrated beyond its saturation point. Because the nucleation rate cannot be measured directly, we use the indirect measurement like induction time, which is the most significant pH drop in the experiment to describe the nucleation rate, which is inversely proportional to nucleation rate. Actually, we made a regression and analysis, which is nonlinear for the kinetic model to some regression constant like K1 and K2. Then we reduce that nonlinear regression model to a linear regression model to some mathematics. Then we needed to calculate the K1 and K2 as our regression constant. In the experimental procedure, we did some magnetically stirring for calcium hydroxide solution. Then we added orthophosphoric acid dropwise with our mechanical agitation setup. Then we mixed our solution for 30 minutes with ultrasonic styrene. When we adjusted the final pH to 10 with ammonium hydroxide, then we recorded the pH variation. Most importantly, we finally obtained a constant pH suspension. After 44-hour aging, we did the instrumentation analysis for our samples. In the analytical calculation, we used 5 samples for different precursor concentration with the calcium to phosphorus molar ratio maintained at 1.7 for all samples. As you see, the highest ionic strength is observed for the sample number 5 with the lowest supersaturation. Accordingly, sample number 1 has the highest supersaturation based on the analytical calculations. As you see, the experiment will result in some pH curves. Based on these pH curves, we drawn a induction time graph for samples, 5 samples. As you see, the lowest induction time has been recorded for the sample number 1 with the highest supersaturation. It is the expectation derived from the kinetic model. Basically, in the statistical validation process, we determine the kinetic constant K1 and K2 from the regression analysis. Then we did the experimental validation. In the experimental validation, basically the laser particle analyzer was predominant. Here, we saw some normal distribution for each and every sample. Basically, the sample number 1 has the narrowest particle size distribution, while sample number 5 shows the broadest distribution with respect to sample number 1. Coming from sample number 1 to 5, we see there is a particle size increment in the size distribution. Then we fitted our size distribution into Gaussian curves with highest accuracy. Then we saw the variation of central tendencies in each and every sample. As you see, the highest central tendencies are recorded for the sample number 5 with the lowest supersaturation. As you see, this scanning lepton microscopy images. It is experimentally proven that sample number 5 has the largest particle size compared to sample number 1 with nano range particle sizes. It is a kind of experimental validation for the regression model. In the DAX analysis part, so that the calcium to phosphorus molar ratio initially was near at 1.56, but after aging, it has increased to 1.7, which is the characteristic ratio for the hydroxyapatite. We can assume that the hydroxyapatite formation happens not to a single step, but some multiple steps. In the FTIR analysis, we have seen all the characteristic bands for the hydroxyapatite confirmed formed crystal-less hydroxyapatite, and also there are some carbonate incorporations in the crystal structure, but it is not harmful to biological hydroxyapatite because naturally available materials in our heart tissue also has some carbonate incorporation. We assume that carbonate coming from the atmospheric carbon dioxide to the crystal structure. We applied this model in some nucleation aspects, basically to determine the interfacial tension with the determined kinetic constant. Then, based on that kinetic constant, we calculated the critical radius for all samples. Sample number 1 has the lowest critical radius, and sample number 5 has the highest critical radius. So critical radius is the smallest particle size which can survive in the solution. In the conclusion, we can conclude direct measurement is not possible for the nucleation rate, so induction time is a good alternative. Then we can derive this relationship, and we can use this relationship for some modeling purposes. In the increased supersaturation and increased temperature and decreased interfacial tension were proven in favor in finer particle sizes. Finally, in collaboration of results with the statistically validated model, the critical radius approach was well suited for the explanation purposes. Finally, we did the publication under KDU 14th International Research Conference with the same title, and some future works are there with extending ripening hydroxyapatite mechanism to the nucleation mechanism. Additionally, then the biological characteristic was to be checked. Some are references here. And finally, I acknowledge the technical staff in the Department of Material Science and Engineering to make this project a success. Thank you, everyone.
Thank you, Mr. G.S. Dhananjaya. So the floor is open for any questions. You can actually leave your question in the chat box, or you can directly ask the presenter. So the presenter, either Mr. G.S. Dhananjaya or Mr. D. Madhusankar is available. So are we audible to you?
Hello, sir.
Yes, Dumindu. Yeah. So Dumindu, so I have one question to you. Can you please tell me what are the difficulties that you have faced when you do this particular research?
It's a good question. In here, we have faced a lot of difficulties because we are doing this research.
Can you talk louder? Yeah. Can you talk louder? Yeah.
Yes. We are doing this research in a very critical situation. We face a pandemic, so we have to face some difficulties such as we can't find some experiment chemicals. This is the main thing we have faced, and something else we can't. We could never do this experiment as we expect because the timeline is getting short. So we rescheduled our research, and we limit our research. If we able to do this, we are planning to do the biocompatible testings.
Okay. Okay, Dumindu. So may I know what are the practical applications? There are certain industrialists who are participating in this particular symposium. Can you elaborate the industrially and practical applications? So what are the, I mean, if it is still long way to go, how do you actually practically apply your work that you have just presented in the future, or what are the any plans and how it is related to the industry? So later on, if any of the industrialists who are interested may actually contact you to proceed further. So can you elaborate on that, please?
The hydroxyapatite is the base compound that we make in bones here. So we can use this material as a bone filler. This in scaffold. We can apply this material and glue the bone because in previous research they have done in this hydroxyapatite in micro. So it's not very biocompatible and it's not naturally growing. When we come to the nanohydroxyapatite, the nanohydroxyapatites has property to naturally grow. So we can apply this material to made for artificial bones. That's the main application that we identify in this research.
So looks like we have no questions raised. So actually, this area is actually was supervised by Professor S.U. Adhikari. So later on, actually, we will be putting this webinar available for everybody to see. So anybody who come across certain questions, especially in the industry, who is related to this particular area, you can easily contact Professor S.U. Adhikari and these two students, and then get some insight into this, and then lead to develop your own industrial problems representing this particular expertise area. So thank you very much, Dumindu, for this particular for this particular answering these questions and your availability.
Thank you.
Okay. Other presentation, the next presentation will be presented by Ms. V.S. Rajapaksa, and the other member is Mr. W.M.D.S. Varnakula Surya. And the presentation title is Modeling of Laser-Assisted Thermal Reduction of Graphite Oxide for the Development of a Strain Gauge.
Hey to you all, I'm Vadisha Rajapaksha from Department of Material Science and Engineering. Today I'm going to present our final year project under the topic Modeling of Laser Assisted Thermal Reduction of Graphene Oxide for the Development of Strain Gauge. First, I would like to give an introduction to our project. Problem definition. Graphene is one of the most promising materials used in electronic industry due to its unique electrical and thermal properties. But it is such a challenging task to produce pure graphene. Reduced graphene oxide can be used as a substitute for graphene because reduced graphene oxide has similar properties as graphene. There are several methods to form reduced graphene oxide, such as chemical reduction and thermal reduction. Many researchers have proceeded experiments to develop graphene-based strain gauges using reduced graphene oxide. Graphene thin films with particular patterning can be easily fabricated by laser-assisted thermal reduction of graphene oxide. The purpose of this work is to model laser-assisted thermal reduction process of graphene oxide in microscale and evaluate reduction degree and electrical conductivity of final product in order to develop a manufacturing process for electronic devices. Our major objectives were modeling the temperature distribution of graphene oxide during irradiation by using commercially available lasers, and developing reaction kinetics based mathematical model to calculate oxygen percentage and the electrical conductivity of laser treated graphene oxide. As first step, we calculated heat dissipation of graphene oxide films considering conduction and radiation. Then we modeled temperature distribution by considering boundary conditions and laser parameters and design parameters. Then we modeled temperature variation on focus point, temperature distribution along the surface through focus point, and temperature distribution along depth through focus point. With the results of temperature distribution modeling, we modeled reduction kinetics. There, we used Lerf and Klinovsky model of graphene oxide, and we found a suitable temperature range, and the reaction occurred at that temperature range for kinetics calculations. With the results of kinetic calculations, we calculated carbon to oxygen ratio in order to find the electrical conductivity of reduced graphene oxide. When we comes to graphene oxide, it is an oxidized form of graphene. It contains oxygen functional groups such as hydroxyls, epoxies, carbonyls and carboxyls. For our project, we used Lerf and Klinowski model of graphene oxide. According to this model, the oxygen groups can be categorized into two components, major components and minor components. Major components are distributed on the basal plane of graphene oxide, commonly hydroxyls and epoxies. Minor components are distributed at the edge of the basal plane, commonly carbonyls and carboxyls. Then we did literature survey for reduction temperature range. At lower temperatures such as 450 Kelvin, hydroxyls, carboxyls and carbonyls try to reduce. Then at higher temperatures, normally above 823 Kelvin, epoxy groups and carbon atoms tends to remove. This reduction of carbon atoms make RGO less conductive. Therefore, we selected our reduction temperature range as 450 Kelvin to 823 Kelvin. As next step of our project, we did temperature distribution modeling. We considered heat transferring happened according to two methods: conduction through the graphene oxide layer, radiation to the environment. Here we assume several assumptions. First one is graphene oxide is an isotropic material. This was assumed considering multilayer polycrystalline behavior of graphene oxide. Then we assumed scattering and reflection of laser beam is neglected, and average laser power was considered as continuous. By using heat conduction equations and considering non-steady state, governing equation was derived, which is shown in the slide. Then for three-dimensional temperature distribution of graphene oxide film, we used COMSOL multiphysics software for modeling purpose. We selected several wavelengths and powers for our project. Wavelengths were selected in the range of 350 to 650 nanometers. Powers were selected in the range of 0.5 to 5 watt. Then we plotted temperature versus power for different wavelengths in the time period of 60 seconds in order to find suitable laser combination. Here we used our lower bound for the reaction as 450 Kelvin and the upper bound for the reaction as 823 Kelvin. Selected laser combinations were used for reduction and temperature distributions along the surface of the graphene oxide film were separately plotted. Then resultant graph was generated in order to find diameter of reduction area according to the laser power. As next step of our project, we modeled reaction kinetics using the results of temperature distribution modeling. Here we used rate equation and Arrhenius equation for calculations. We considered modified Lerf and Klinowski model of graphene oxide for our purpose. This model represents chain-like structure of graphene oxide considering the unit cell as C6O2OH twice. For theoretical calculations, functional groups at edges of the graphene oxide plane such as carboxyls and carbonyls are neglected. We separately calculated reaction kinetics for selected wavelengths and powers. Then we plotted graphs in order to find maximum reduction for different parameters and carbon to oxygen ratio for different lasers. As final step of our project, We did calculations to find electrical conductivity achieved by selected laser powers and wavelengths. We did literature survey to find the relationship between carbon to oxygen ratio and electrical conductivity of reduced graphene oxide. So, electrical conductivity values were taken from the graph shown in the slide according to our oxygen content values. So, we plotted graphs to find maximum conductivity at irradiation point for several powers and average conductivity of irradiation area for several powers. Maximum conductivity was achieved as 8 Siemens per centimeter and maximum average conductivity was achieved as 8 Siemens per square centimeter for laser power of 5 watt and wavelength of 550 nanometers. This value lies in the semiconductor range. Major parameter for strain gauge is electrical resistivity. Therefore, this method is suitable to make graphene oxide patterns in order to develop a strain gauge. In summary, we developed a model to predict distribution of carbon to oxygen ratio and electrical conductivity of laser-assisted reduction of graphene oxide. Reduction volume diameter of different laser parameters were calculated in order to assist controlling the resolution in industrial applications. Maximum carbon to oxygen ratio was improved from 1.5 to 3.5 comparing to initial state. Electrical conductivity is improved from insulative region to semiconductive region. This is the end of our presentation. I sincerely appreciate your attention today. Thank you for your kind cooperation.
Presentation. Ms. V.H. Rajapaksha, are you available online?
Rajapaksa is not available, sir, but Varnakula Surya is available.
Okay. Mr. Varnakula Surya, so so Mr. Dilip, again I have certain questions to you. So let me share the screen with the project title. So actually, now again I'm asking a question. What is the practical application of your project? I mean, how the industry can be actually, getting advantages from your research. Can you elaborate on that? Hello? Am I audible to you, Mr. Varnakula Surya? Looks like I can't hear you.
Now it's audible, sir. Can you?
Yeah. Now it's audible. Yes, go on.
Yes. I can't hear. I cannot hear the question. Can you please?
Okay, I will repeat. What is the Dilip? What is the practical applications and what are the advantages for the industrialist from your research? Can you elaborate on that? Because if there are certain industrial people, they can get some aspect on that.
Yes, actually, graphene can be used as used as the alternative materials for electronic devices, because graphene is the graphene has the highest electrical conductivity.
Yes.
Here we manufacture graphene using graphene oxide, because the pure graphene manufacturing of pure graphene is quite difficult task. But using using graphene oxide, we can manufacture graphene very easiest method. And here we can be used to manufacture electronic devices. Patterns. Can you hear?
Yeah, we lost you at several points, but anyway, go on.
Okay.
Yeah.
Okay. Actually, here the industrial usage is the graphene this method we can develop graphene by ECS method, because the manufacturing of pure graphene is something difficult task, but using graphene oxide we can manufacture conductive graphene, and the laser assisted thermal reduction process can be used to manufacture uh, some specific and complex conductive patterns. For the most electronic devices we require electrical patterns like a strain gauge. It is something very complex patterns there. So using conductive patterns, that is the basically industrial usage of this process, this project works.
Okay. So that means you can actually make very accurate and efficient strain gauges using your suggested methods, right?
Yes, of course.
Okay, okay. So yeah, that's the good news. And what are the practical difficulties that you have actually faced during when you go through the now actually your project is about actually modeling. So before the modeling, did you have any plan to do some actual practical I mean implementation of and test it?
Yes, of course, because initially the project work was basically it is dependent on practical. We are planned to develop a strain gauge using this method in practically, and in the first stages we analyze the feasibility and everything we analyze. But due to this COVID-19 situation, we have to change the this project work for the modeling side. That's a major difficulty. But earlier stage we plan to do this project, and this method is very easy to elaborate, easy to do that in the university, our Sri Lankan universities, because there are no too much technical things. Only basically the process is very simple. You only need laser and the 2D patterns to print the 2D patterns.
Okay.
Therefore, first stage we plan to do the experiment, but unfortunately we unable to do.
Okay. Okay, Mr. Dilip. And what are the software that you have used to do this modeling?
Here we use COMSOL multiphysics software for
Okay.
the temperature distribution analysis.
Hmm.
That's the major software we use here.
Okay, okay. So, so I'm awaiting any more questions from the participants. If you have any questions, please feel free to ask from Mr. Dileepa. Okay, so thank you, Mr. Dileepa, for your time and I mean accurate, I mean very clear answers. I mean this will clear any doubts to the industrialists and other participants in the forum. So thank you, Mr. Dileepa, again for your time.
Thank you, sir, and thank you everyone listening our project work.
Yeah, okay, you're welcome then. Okay, so our next project title will be presented by Mr. D.M.L.Y. Samarakon, and it has the project title as MIE theory based investigation of the effect of size distribution on the surface plasmonic absorbance of silver nanoparticle. So it will be presented by Mr. D.M.L.Y. Samarakon.
D.M.L.Y. Samarakon. My research partner is DLHPP Dahalal. We are from Department of Materials and Engineering in University of Moratuwa. Our supervisors are Senior Lecturer Mr. Bandhu Samarasekara and Senior Lecturer Dr. Shanta Amarasinghe in our department. Our final year research topic is ME theory based investigation of the effect of the size distribution on the surface plasmonic absorbance of silver nanoparticles. In recent years, silver nanoparticles have attracted a lot of attention due to their good conductivity, chemical stability, use as catalyst, and their application in various industries including the medical science to deal with food and drug industry packaging, antimicrobial properties, and also their unique electrical and optical qualities. Surface plasmonic resonance is a powerful technique to retrieve information about the optical properties of biomaterial and nanomaterial. The surface plasmon absorbance and its characterization values are very important data for various applications today. If the surface plasmon absorbance band can be theoretically generated and its characterization curves can be theoretically calculated, it is very important for future application technologies. Furthermore, if the software tool can be developed based on these mathematical calculations, it is very advantageous for many sites. These are the objectives of our research. First one, develop a theoretical framework to express the extension cross-section of small silver particle based on Mie theory. Second one, develop a software code to solve the equation. Next one, create a software tool using developed software code. Last one, investigate the effect of the size distribution on the surface plasmonic absorbance of silver nanoparticle using the software tool. Okay, next let's see methodology in our research. Our research methodology based on mainly three parts. First one, developing mathematical model. Second one, developing software code. Final one, developing software tools. Okay, now let's focus on developing mathematical model. Localized surface plasmon resonance are non-propagating collective excitation of the conduction electrons. Extended Dur theory was used here to mathematically model these surface plasmon resonance of silver nanoparticles. Here we consider spherical shaped particles. If the particles are not very large compared to the mean free path of the conduction electrons, then their optical constant becomes a function of the particle size. The complex dielectric constant of silver particle can be written in this form of two components. This dielectric constant of the silver particle can be described by the extended Dur theory. You can see it this equation. In nanoparticle, the mean free path conduction electrons is reduced due to collision of electrons with the particle surface. So according to Mathesian's rule, the total frequency can be described like have been mentioned. And this is represented by an additional term, static collision time of nanoparticle. It can be described by using radius and Fermi velocity. So we can say the effective mean free path of an electron in a nanometal particle is a function of the radius of the particle. Then nanoparticles' optical constant become a function of the particle size. It is fully explained as have been mentioned. The extinction cross-sectional of a small spherical particle immersed in a medium with refractive index at wavelength can be described using the Mie theory. We can use it for calculate extinction cross-sectional of nanoparticles. The scattering coefficients in terms of Riccati-Bessel function solutions. It can be described like have been mentioned. Then we selected MATLAB program for calculated extinction cross-sectional of nanoparticles. Solution of Riccati-Bessel function were not included as MATLAB standard function, but solution of ordinary Bessel function were included as MATLAB standard function. These are solution of spherical Bessel function from solution of ordinary Bessel function. If the silver nanoparticles are dispersed in a homogeneous medium and the interparticle interaction are negligible, then the extinction cross-section can be modeled as the optical response of one immersed nanoparticle times the particle number density. The extinction is the sum of absorption and scattering cross-sectional of single particle. The calculated extinction coefficient can be mapped to experimentally observe absorption for a dilute spherical nanoparticle dispersion and number density of particle per unit volume needed to calculating total absorbance value in solution. This part is discussed how to software code was developed using the mathematical model in the previous part. So computer application was needed for done this work. The MATLAB computer program was selected. Firstly, a MATLAB code was developed to calculate the extinction cross-section. Then this MATLAB code was developed for getting surface plasmon absorbance value under mainly two different scenarios. First one, the MATLAB code was developed for calculate surface plasmon absorbance in a single nanoparticle in given spectrum window. Then this MATLAB code was extended to calculate absorbance band for given particle size variation. Then it was extended to obtain the characteristic of the surface plasmon band for silver nanoparticle, such as how to change the maximum absorbance width radius, how to change the peak position width radius, and how to change the pull width at half maximum absorbance width radius. Second one, practically it's not possible to prepare the nanoparticle solution in as nanoparticle of same radius. A nanoparticle solution can be permutated with the particle size distribution. So the MATLAB code was developed to get the absorbance band and fundamental curves for particle size distribution. Then deviation could be reduced between our theoretical result and experimental data. Then this MATLAB code was extended to get absorbance band for distribution parameter variation. Then this result was theoretical calculated to obtain characterization curves in surface plasmon absorbance in silver nanoparticle solution with distribution variations. This is a final part of methodology in our research as developing software tools. We will introduce a new software tool. Its name is Me Investigator. These software tools have been designed by using MATLAB code previously mentioned. Surface plasmonic resonance analysis technique mostly used for bioengineering and modern chemistry and physics technology. Surface plasmonic analysis is a complex mathematical based technique. Therefore, we developed software tool for analyzing surface plasmonic resonance of metallic nanoparticle. This software tool called Me Investigator. This software tool can be used to single particle analysis and multi-particle analysis. The developed software tool we call Me Investigator has mainly two analyzers. First one is a single particle analyzer. It has two analyses, single particle analyzer and particle size variation analyzer. Second one is a multi-particle analyzer. It has two analyzers, single distribution analyzer and multi-distribution analyzer. Okay, let's move to the result and discussion part of our research. The peak position, maximum absorbance and bandwidth at half maximum absorbance are the fundamental characteristics of the surface plasmon absorbance band. The Me Investigator software tools can be used to obtain surface plasmon absorbance band and get its characterization curves. So this section was discussed what are the results of these four Me Investigator software tools. Then investigate effect of the particle size distribution on the surface plasmonic absorbance of silver nanoparticle using the software tool result. Mainly this part is divided into four scenarios. First one was the result of Me Investigator single particle analyzer. This is a graphical user interface of Me Investigator single particle analyzer. This tool can be used analyzes surface plasmon absorbance spectrum with given particle radius and given surrounding medium refractive index. Before the analysis, we need to define spectrum window. Analyzing doing under these spectrum window. As an example, inputs are shown this figure. One was the result of investigator particle size variation analyzer. This is the graphical interface of investigator particle size. This tool can be used to analyzing plasmonic absorbance band and fundamental curves for particle size variation. Before the analysis, we need to define spectrum window, size parameter range, and refractive index of surrounding medium. As an example, inputs are shown this figure. When after inputs value, we can get characterization curves using this software tool. Third one was the result of Me Investigator single distribution analyzer. This is a graphical user interface of Me Investigator single distribution analyzer. This tool can be used to analyze surface plasmon absorbance spectrum and fundamental curves for particle size distribution. Before the analysis, we need to define spectrum window, size parameter range, distribution parameters, surrounding medium refractive index and distribution type. As an example, inputs are shown this figure. When after inputs values, we can get characterization curves using this software tool. Fourth one was the result of Me Investigator multi-distribution analyzer. This is a graphical user interface of Me Investigator multi-distribution analyzer. This tool can be used to analyze plasmonic absorbance curve and fundamental curves for more particle size distribution. Before the analysis, we need to define spectrum window, size parameter range, distribution parameters, surrounding medium refractive index, and distribution type. As an example, inputs are shown this figure. When after inputs value, we can get characterization curves using this software tool. Okay, let's move to the conclusion part in our research. Mainly, this study was presented for software tools, a flexible virtual laboratory designed by combining several algorithm models and techniques into computational platform, and develop software capable of analyzing plasmonic absorption spectrum of single particle and particle size distribution. Furthermore, this work was presented a theoretical framework and MATLAB code can be used for theoretical calculate surface plasmon absorbance curve and fundamental characterization curves. Finally, this study was tried how to size distribution effect for surface plasmon absorbance band for silver nanoparticle solution using software result. We were generated surface plasmon absorbance band and fundamental characterization curves using software tools, but changed only distribution parameters and hold other all parameters. These results were mentioned previously. According to these results, we could investigate the size distribution of the silver nano solution mainly affect on surface plasmon absorption band. This is a key output of our research, introducing a new software tool. Surface plasmon resonance is a very powerful technique to retrieve information about the optical properties of biomaterial and nanomaterial. So this technique mostly uses bioengineering and modern chemistry and physics technologies. But surface plasmonic analysis is complex mathematical based technique. So we introduce a new software tool for analyzing surface plasmonic absorption. We call it Me Investigator. Thank you.
Okay, thank you, Mr. DMLY Sambapon. Mr. Sambapon, are you available for quick Q&A? Yes, okay. Mr. Lalendra Samarakon, so thank you very much for your presentation titled MI theory-based investigation of the effect of size distribution on the surface plasmonic absorbance of silver nanoparticles. So the forum is open for any questions from Mr. Samarakon. So, Mr. Samarakon, again, I have several questions to you. So yeah, it looks like your project actually is mainly based on, I mean, it's a complete modeling aspect. What are the software that you have used in this particular project?
Mainly, mainly used the MATLAB program, and MATLAB features is a designer program. So these two softwares.
Okay, so what are the other? I mean, especially you have developed an app, right?
Yeah.
So what is the use of this app, Mr. Lalendra? You elaborate on that. I mean, there are maybe who are the industrialists who are interested on that, and how do we use this app, and what is the purpose?
Yeah, okay. Our investigation was the how to affect the particle size distribution on surface plasmonic absorbance band. So we found that the particle size distribution mainly affect the surface plasmon band. Furthermore, so we presented software tool which we can theoretically calculate how much affects size distribution of the surface plasmonic band. So surface plasmon resonance is a very advanced technique to retrieve information about the optical properties of biomaterial and nanomaterial. So these surface plasmonic resonance has mainly applications today. For example, surface plasmon resonance technique mainly use optical sensors industry. So they want to find out correct particle size distribution with given suitable surface plasmonic band. So they can calculate theoretical using software tool. It is a very cost effectively and without during experimental. And so another is the optical light microscopy is the most available in my laboratory. So dynamic light scattering spectroscopy is not most available. So we need to find what is the size particle size distribution. We can found it using dynamic light scattering spectroscopy, but this software tool use an light optical light microscopy. We can found out what is the particles distribution on nanoparticles. So these are the main usages and application in our related with our research.
Okay, Mr. Lion, thank you very much. Actually, now before the pandemic been started, may I know, did you have any plan to any plan to do some experimental activities? I mean, did you have any?
Yeah. Firstly, we plan to doing this project with related with the practical, experimental and experimental method. But this pandemic situation, we mainly focus on the theoretical method with modeling part. So next we can next level develop this research project. We can doing this validation part on this software tool. Doing experimental, doing experimental and get result. So next level we can do it.
Okay. Okay, thank you, Mr. Lalendra Samarakon, for your presentation, and it has been partner, Mr. Dayalal. And if there is any person who is interested on this work, you can contact, I mean, the supervisors and the students, Mr. AMPB Samarasekara and Dr. D.A. Samarasinghe, who are the senior lecturers of the department. So you can ask more details if you are interested in this.
Okay.
So
Thank
you very much, Mr. Lalendra, for your time.
Thank you. Thank you very much, all of you.
Okay. So our next presentation is will be delivered by Miss J. Lingaratnam, V. Lingaratnam, and the project partner is Miss J. Lavanya, and the project title is about investigation of electrical properties of microcrystalline cellulose-based composite material.
Done research under Mr. Bandhu sir and Dr. Amara Singh sir under the research topic of investigation of electrical properties of microcellulose-based composites. The future of polypropylene composite in market looks good, and it is expected to reach an estimated cost of $657 million by 2021. Out of the total thermoplastics, polyethylene has higher market value, but market growth rate is higher for polypropylene composite, and it will surpass polyethylene in few years. The major drivers for market growth rate of polypropylene composite are the increasing use of lightweight materials and benefits of reinforced polypropylene composites over metals and pure plastics in its performance. Furthermore, lower cost of manufacturing, high strength, no curing, reprocessing flexibility, high temperature resistance will also drive the market growth rate of polypropylene composite. Uses of polypropylene composite include products related to transportation, consumer goods, electric and electronic industries, and some more applications. When considering polypropylene usage in different applications, electric and electronic products possess major percentage in the last 6 years, and we can observe that in the chart given here. When considering products such as food packaging material, we only need to consider mechanical and thermal properties. But in applications such as insulation material and dielectric medium, it's better to consider electrical properties of composites, as electrical properties have great influence on electrical applications. We can take insulation material of HVDC cable and dielectric medium of capacitor as the application in which we can use polypropylene composites. When considering insulation material of HVDC cable, we need to get a material with the following properties: high breakdown strength, low dielectric constant, low dielectric permittivity, and high DC volume resistivity. HVDC cable transmission has drawn increased attention due to great development in high voltage power transmission technology in recent years. Currently, polymer-based materials are largely used in various high volt apparatus such as power transformers, insulators, capacitors, reactors, surge arresters, current and voltage sensors, power cable, and terminations. Polyethylene has been widely used as the insulation material for high voltage power cables owing to its good properties. Due to those enhanced properties, polyethylene has a choice for HVDC cable insulation material over last decades. However, polyethylene suffers some serious drawbacks as an insulating material for HVDC cable, such as undesirable space accumulation, long processing time, high production cost, and non-recyclability. So the industry is seeking for another best option for HVDC cable insulation. And when considering dielectric medium of capacitor, the material must have the ability to support the dielectric fields while dissipating minimal energy in the form of heat, and lower the dielectric loss of the material, the more effective the dielectric will be for the application. A dielectric material means that will conduct electricity with very low performance, but it will essentially support the performance of electrostatic field. Electrostatic electrical field can accumulate energy to a minimum in situations where the flow of current between oppositely charged poles does not interrupt the dielectric flux lines. This property helps capacitor. That's why we need a material which supports dielectric field while dissipating minimal energy in the form of heat. The lower the dielectric loss, the more effective the dielectric will be for the application. In our project, we investigate the electrical properties of microcellulose-based polypropylene composite for investigating the potential for electric applications. As far in the research field, electrical properties of composites are analyzed, but not for microcellulose-based polypropylene composites. One specific feature in our research is prepared composite is an environmental friendly material, and we investigate the possibility of modifying MCC using green surface modification methods. Usage of green surface modification method for modifying microcellulose, which is a reinforcing material in our research, will change the non-biodegradable polymer composite into a biodegradable composite. As I mentioned earlier, why we have done this project was to understand the change of electrical properties and investigate the potential of surface modified MCC based composites for electric insulation applications. We are going to ensure that we can use microcellulose based composite as a material for producing insulation material and give appropriate product performance. Moving on to methodology, here I mentioned in which path we travel to do the project in an efficient manner. In our methodology, I want to mention a few things. For the characterization of MCC, we use three methods: FTIR, SEM analysis, and hydrophobicity test. And we measured the electrical properties with different composition and different frequencies. Parameters which we measured in LCR meter were dissipation factor and capacitance. The electrical properties which we considered in the research were dielectric constant, dielectric loss, and AC electrical conductivity. The results that we gained are lower dielectric constant and dielectric loss were achieved by the polypropylene composite with 1% microcellulose composition and in the frequency range of 50 Hz to 5 MHz at room temperature, and higher values of dielectric constant and dielectric loss were obtained by the composite with 5% microcellulose composition. in the frequency range of 50 Hz to 5 MHz at the room temperature. So, MCC-based polypropylene composite open up for new opportunities in the applications such as insulation material for HVDC cable. Before I finish, I like to leave you with one final thought. The recent development in the field of HVDC cable insulation demands for a high-performance, eco-friendly insulation material. Polypropylene, due to its superior electric and thermal properties, has gained greater attention in the field of HVDC cable insulation, and it is expected to be a good alternative in replacing conventional polyethylene in HVDC cable insulation. It can be a challenge to achieve homogeneous dispersion of microfiller in the polymer matrix, especially at the industrial scale. Therefore, the development of advanced materials, mixing tools, and chemical formulation strategies in transitioning research achievements at the laboratory scale to the industrial scale will be crucial in determining successful implementation of polypropylene composite as future HVDC cable insulation. Thank you very much.
Okay, thank you very much, Julsa, for your presentation, and the project partner is Lavanya, and we go to the title page. Yes. So the floor is open for any questions. If you have any questions, please feel free to ask. Ms. Vidusha, you are with us, right?
Yes, sir, I can hear.
Okay. Okay, Ms. Vidusha, again, as usually, I have another question. Now, this you have actually kind of a new material introduced for electrical applications, right? Is it so?
Yeah.
Yeah. Okay. So, do you think that this particular application that you have investigate, or is it now ready for industrial deployment, or what are the next steps that you have planned? In the future, what are the things that you have planned for any future directions of this?
So, now they are using polyethylene composites, but as they are facing more defects and challenges in polyethylene, they are planning to replace in the industry. So there's a chance for taking polypropylene composite in the market in an industrial scale. We have done in the laboratories.
So that
because
means
our composite.
Yeah.
Can load nowadays they are using polyethylene composite. So can that our composite has more temperature tolerance and have low dielectrics loss. So it will be useful for in the application of electrical properties.
Okay. So did you identify? With respect to industrial application, did you now? I have seen that you have identified several industrial areas where this particular path will be, applicable. So if it is ready to implement, do you have any idea to contact some of these industrialists to show your research, and are there any plans?
No, sir. No,
Okay,
we don't have any contact with the industry people.
Okay, right. So looks like your research is basically, have ample amount of experimental work, right?
Yes, sir.
Yeah. So what are the challenges that you have faced when you do this, during your course of doing these experiments?
Yes, sir. Yes, sir. We were given only 2 weeks due to the COVID-19 restrictions, so we couldn't be able to experiment for enough lot of samples. So anyhow, we tested for limited number of samples, so which is enough to come to the conclusion. And other thing is the 2 week is not enough for us to measure more electrical properties like space charge behavior and dielectric breakdown strength.
Okay, okay.
Yeah, in so we are planning to do in future. We have to experiment for more properties to come to the
Okay,
accurate conclusion.
right. Yeah, are there any more questions to lead into Ms. Vidusha? Okay, so thank you, Ms. Vidusha, for your time, for your presentation. And if there is any person who is interested in this particular area, you can actually contact again the supervisors, Mr. Pandu Samarasekar and Dr. Shant Amarasinghe, who has supervised this project, and also these students, Ms. Vidusha Lingaratnam and Ms. Lavanya. Okay, thank you, Ms. Vidusha, for your presentation.
Thank you so much.
Yeah, okay. So it leads to our last presentation of technical session 1, which will be delivered by Mr. Sadeepa Amaratunga and his project partner, Mr. J. Malshan, and the project title is double layer capacitor based model for super capacitor.
I'm Sadeep Amaratunga from the Department of Materials Science and Engineering. I'm going to present about our final year research project titled Double Layer Capacitor Based Model for Supercapacitors. Supercapacitors have attracted a lot of attention because of their unique quality of fast charging and discharging capability, high power density, and long service life. Easy fabrication and lightweight make supercapacitors suitable for a wide range of applications as electrical energy storage devices. Supercapacitors are taking place of batteries and conventional capacitors in many applications like portable electronics, backup power supply, smart grids, memory backup, and hybrid vehicles. Carbon-based supercapacitors are promising large power devices that keep on dominating the commercial market, holding fascinating features such as fast passes of energy, millions of charge-discharge cycles, wide operational temperature, and high Coulombic efficiency. They consist of two carbonaceous electrodes soaked in an electrolyte and porous membrane separator. The energy storage mechanism is reversible charge separation at each interface of the electrolyte with the cathode to anode surface, which forms two closely spaced charge layers. The corresponding double layer capacitance arises from the minimal separation distance and large interfacial area. The major challenge for supercapacitors with aqueous electrolytes when compared to batteries and fuel cells is the insufficient energy density. The equation for energy density shows that the capacitance and the square of the voltage are directly proportional to the energy density. So increasing either one or both of them is the effective way to increase the energy density. There are many attempts so far to increase the operating voltage, but when coming into aqueous electrolytes, operating voltage cannot be increased effectively due to the lower electrochemical stable potential windows of aqueous electrolytes. Therefore, improving the capacitance of the supercapacitors with aqueous electrolytes should be focused in order to increase the energy density. Here we are focusing on improving the porous carbon electrodes of the supercapacitor in order to increase its capacitance and modeling the changes of the capacitance behavior of the cell according to the various surface roughness topologies of the porous electrode material. In order to achieve this, first we have to determine the potential distribution profile around the electrode surface. Therefore, the objectives of our research are solving the linear Poisson-Boltzmann equation numerically to predict the potential distribution of the diffuse layer for a 1D rough electrode surface and developing a method to predict the dependence of the double layer capacitance on the roughness profile of the electrode surface using Poisson-Boltzmann theory and the Stern theory. The significance of our study is that we are determining the effect of the electrode surface roughness on the capacitance of supercapacitor quantitatively. With our effort, An experimentalist can predict the variation of the double-layer capacitance of a supercapacitor according to the changes done for the electrode surface roughness. Because of that, they can determine the most effective surface roughness factor of the electrode for the supercapacitor, which they are going to fabricate before doing any experimental work. For quantitative analysis, we are using a numerical approach which makes our study differ from most of the other studies done so far. This is the path we followed in achieving those objectives. First, we determine the characteristic roughness factor for the roughness profile we selected for use solving the Poisson-Boltzmann equation. Then we had to determine the boundary conditions for solving Poisson-Boltzmann equation in RK4 method. Then we obtain a relationship between the differential capacitance and the roughness factor. And finally, we verified the obtained results by comparing the graphs we got by plotting the equations derived mathematically from the MATLAB software with the plots for different types of electrode surfaces which are available in the literature. When talking about the procedure, first we define the basic unit of the 1D roughness profile, and the roughness factor R is determined. For the purpose of reducing complexities in the derivations, we are using the linearized version of the Poisson-Boltzmann equation, which have been done in most of the available literature. Poisson-Boltzmann equation has no exact analytical solution according to the literature. Therefore, it should be solved numerically. We selected Rangekata fourth order method to solve it numerically. This is the method we used to solve the linearized Poisson-Boltzmann equation in numerically using RK4 method. Since this is a second order differential equation, first it has to be separated into two first order differential equations. Here, the range which we are considering in our case is the distance from the electrode surface to the point of consideration, and it is divided into number of steps, of which the step size is h. Further we reduce h, we can get more accurate results. These calculations are repeating in a number of times when calculating the potential of a single point. So when determining the potential distribution, we have to calculate the potential of huge numbers of points within double layer depending on the step size h we select. Therefore, we use MATLAB to solve the equation by writing a loop to execute these repetitive calculations. Since we used a very small step size, it took a huge time for the program to run, and finally we got the potential distribution of the diffuse layer as expected. Differential capacitance is determined by differentiating the charge density in terms of the potential. So accordingly, we were able to obtain this equation for the differential equation capacitance of the diffuse layer through a series of mathematical derivations. We consider the 1:1 symmetric electrolyte, aqueous electrolyte with a very low concentration to our work. The concentration of the electrolyte used for calculations is 0.001 moles per cubic decimeter, and the applied voltage range was below 5 millivolts. These values are used because we developed the theory of effect of electrode roughness on the double layer capacitance based on Stern model, which is valid in lower electrolyte concentrations and applied potential. According to the Stern model, the electrical double layer is composed of two parts. One is the compact layer consisting inner and outer Helmholtz planes, and the other is the diffuse layer of mobile layers. When going into the results obtained through our numerical calculations, the solution for the Poisson-Boltzmann equation, that means the potential distribution of the diffuse layer with the distance from the electrode surface is plotted here, and it has the characteristic shape of the curve for different diffuse layer potential distribution presented by the Stern model. This graph shows the variation of potential of a point in diffuse layer with the simultaneous variation of roughness height symbol B and the roughness period length symbol A. This graph shows the variation of differential capacitance with roughness height B, and this is the variation of differential capacitance with roughness factor R. The dependence of differential capacitance with the simultaneous variation of B, the roughness height, and the A plus C, which is the length of the roughness profile, is shown here. This graph shows the variation of differential capacitance with simple A, while B and C are kept constant. And this graph shows the variation of differential capacitance with C, while B and A are kept constant. Both of these graphs shows an increment of differential capacitance with a decaying positive gradient when increasing A or C. When considering a 3D structure like this, wherein A can vary the size of nanopore-like structures on the electrode surface, and wherein C can vary the size of nanotube-like structures on the electrode surface. So accordingly, we can predict the quantitative variation of differential capacitance with the nanopore and nanotube sizes on the surface of the electrodes of supercapacitor. The importance of this is that the experimentalists who are dealing with nanoscale electrode surfaces can make use of our method as a base to develop the equations to predict the results of the variation of surface roughness profiles related to their work. And thank you.
Okay, thank you very much, Mr. Sadeepa Amaratunga. Mr. Sadeepa, are you available?
Yes.
Okay, great. Let me go back to the first page of the presentation. Yeah. So, if you have any question, folks, you can ask from Mr. Sadeepa from the presentation. You have any questions? Okay, so that lead me to ask several questions to you, Mr. Sadeepa. Now, is it now AA capacitor-based model for supercapacitors? Now, your project is also kind of computer modeling-based one, is it? Or
yes, basically,
yeah.
we were intending to go to the practical area also, but with the current situation of the country, we couldn't access the land. So we shifted into the theoretical part only.
Yeah. So to enlighten this, the participant, can you just briefly explain what is supercapacitor, how it is used, and what are the advantages of that supercapacitors? And
yes,
yeah.
A supercapacitor, we know about the normal capacitors, normal parallel plate capacitors. In the supercapacitor, as I mentioned in the basic structure in the slide, and it shows it has a chart as in both electrodes. When the electrolyte interface, the charge separation gives the this called double layer capacitance, because the charge separation is the separation distance is very low, and the interface area is very high because of the electrodes we are using. Those electrodes have are very porous, so the interface area is very high in supercapacitors. So that's why we are using very high that's why we are using electrodes with high effective surface area. So according to that basic structure, you can see the charge, the capacitance is coming from the charge separation with the very small distance in angstrom level and the very high surface area. So this applications of this is it can charge or discharge in a very small time by giving a high pulse of energy. Like so, it can be used in hybrid vehicles and such things, which where you need a very sudden high energy.
Okay, clear. What are the software that you have used, Mr. Sadeepa, for your modeling?
Yeah, we use MATLAB basically. For that doing our for our numerical calculations by developing a loop for the repetitive calculations and getting the graphs we needed for the results.
Okay, great. Mr. Sadeepa, one additional question now. Did you identify any industries that where your particular research area can lead to any practical application? Did you identify it in Sri Lanka, or what are the any deployment in application?
Sorry, sir, I couldn't hear.
Yeah, do you have, did you identify any area where you can actually use the model where in the practical aspect?
Yes, actually, I mean, we we were first expecting to actually developed this for the activated carbon because it's an product which is readily available in Sri Lanka and local there are many local manufacturers of activated carbon.
Yeah, absolutely.
Activated carbon is a material which has very great high porosity, and we can actually change their surface topology by various methods like plasma treatments and all. So we were expecting to do such a thing and do this practically to prove our theories correct.
Okay, so are there any additional questions to Mr. Sadeepa from the attendees? Okay, so so if you have any questions with related to this particular topic area, you can again contact the supervisor and the students, Mr. Sadeep Amaratunga and Mr. J. Malchan, and the project supervisor, Dr. Shant Amarasinghe, for more in-depth, for more clarification. So thank you very much, Mr. Sadeep, for your contribution and for your question. So that leads to actually completion of technical session 1. So over to you, the compere is Minuri. Thank you very much.
Thank you very much, sir. And thank you very much for all the participants for your amazing participation. So, ladies and gentlemen, the symposium will now be adjourned for lunch and it will be resumed here in an hour. Thank you very much. Hello, everyone. Welcome back after the lunch. The second technical session of Symposium will be chaired by Senior Lecturer of the Department of Material Science and Engineering, Dr. Mrs. A.S. Galahenage. Over to you, madam.
Okay, thank you, Vinori. This technical session 2, MESI 2021, has 5 recorded talks, and there will be a Q&A session after each talk. And without further ado, let's move into the presentations. Our first presenter is Rana Singha. He will be talking about the simulation and analysis of effect of halide ions of perovskite on perovskite solar cell performance. In simply, this is a project on a kind of solar cell. The Rana Singha, you can play.
Under simulation and analysis of effect of halide ion of perovskite on perovskite solar cell performances was conducted with my colleague Gihan Lakhtar under the supervision of Dr. Asha Gallenagi. And I am Sarit Singh from Department of Material Science and Engineering. Now I will give a brief introduction about this research. Numerical simulation is the best way to investigate about physical mechanism in solar cells without making the device in real world. Simulating solar cells will be cost efficient, fast and convenient way to study in this research field. Solar cell capacitance simulator, also known as SCAPS, was developed by Ghent University, Belgium for simulate silicon solar cells was used to simulate solar cells in this research project. IV characteristics of solar cells and quantum efficiency of solar cells were optimized during this research work. This figure shows crystal structure of the perovskite material. The general formula for perovskite material is ABX3, where A is an organic cation, usually methyl ammonium, B is a bivalent cation, usually lead, and X is a halide ion, usually bromide or iodide. This is the general structure of perovskite solar cell. The perovskite material layer acts as absorbing layer of protons and generating exciton. ETM is the electron transport layer and it supports electrons to reach front contact layer. HTM is the hole transport layer which support hole to reach back contact layer. In this study, we set up two objectives. First, to study the effect of halide ion in the perovskite on perovskite solar cell performances. And the second, to analyze and interpret the effect of absorption layer thickness on photovoltaic properties. Beforehand, we used the SCAP software for our simulation confidently. We tend to verify accuracy of the simulations. So we conducted tests with data available on actual past research and try to get some result with using simulation software. Here the comparison of result that we get with the actual results. In this simulation, we considered one-dimensional model for solar cells. So basic physics behind the simulation software can be simplified to these two equations. The effect of defect density and ionized doping density are not considered in this model. So the Poisson equation can be given by equation 1. The continuity equation of electrons and holes can be described by equation 2. This flowchart shows how the simulation software works for solve above two equations shown in previous slide. Here the result and discussion of our research work. When considering effect of halide ion, there is a significant difference between IV curves when varying the halide part of perovskite material. The short circuit current in methyl ammonium lead iodide is much higher than methyl ammonium lead bromide because the band gap of methyl ammonium lead iodide is less than methyl ammonium lead bromide. This figure shows quantum efficiency versus wavelength graph for methyl ammonium lead iodide and methyl ammonium lead bromide for same layer thickness. The efficiency of methyl ammonium lead iodide solar cell is higher than methyl ammonium lead bromide solar cell because of the optical absorption spectrum of methyl ammonium lead iodide spans in the wavelength range of 400 to 760 nanometer is much broader than the wavelength range of methyl ammonium lead bromide. When considering the effect of the absorption layer thickness, current density increases in both methyl ammonium lead bromide and methyl ammonium lead iodide with the increase of absorption layer thickness because it leads to absorb more photons and it will generate more electron hole pairs. When considering open circuit voltage versus thickness graph, methyl ammonium lead bromide has higher open circuit voltage than the methyl ammonium lead iodide. Because of methyl ammonium lead bromide needs much energy from protons to create charge carriers. The reason for that is methyl ammonium lead bromide has higher relatively band gap than the methyl ammonium lead iodide. In this fill factor versus thickness graph shows quick drop in fill factor in both absorbed material varying with absorbing layer thickness. Fill factor is mainly associated with resistive losses and the shape of the IV curve. Resistive losses increases with the increases of absorbing layer thickness, which consequently leads to a decrease in fill factor. This figure shows efficiency versus thickness graph. When the thickness varied from 0.5 micrometer to 1.2 micrometer, the efficiency increases up to 0.5 micrometer and 0.4 micrometer in methylammonium lead iodide and methylammonium lead bromide respectively. Later it is decreased. Hence, optimized thickness of the absorbing layer thickness are 0.5 micrometer and 0.5 micrometer for both methylammonium lead iodide and methylammonium lead bromide respectively. These are the photovoltaic parameters for both methylammonium lead bromide and methylammonium lead iodide for optimal thicknesses. On this research, we concluded that the halide iron perovskite material largely affect the device performances. Iodide iron gives higher short circuit current efficiency and fill factor, while bromide iron gives higher open circuit voltage. Also, there is an optimal thickness for each type of absorber. Authors would like to acknowledge the great assistance given by supervisor and the academic staff of Department of Material Science and Engineering, University of Moratuwa through the time period. A research paper was derived from the work of this research was presented on Morcon 2021 and now published on IEEE journal. Thank you.
Okay, thank you, Rana Singh, for your nice presentation. And now it's open for questions. Actually, as a supervisor of this presentation, it's not good to ask questions by my side. I appreciate if the audience can raise your questions. Okay, then I'll ask the simple questions, Rana Singh. This is a new kind of solar cell. Then today market available solar cells, what are the difference? Why we need this kind of solar cell types? There are a lot of solar cells available in market, no?
Okay, thank you, madam. This type of solar cells can be quickly manufactured and simply manufactured, and this type can achieve higher efficiency than marketly available solar cell. So I think this is the reason for need of this kind of solar cells.
Okay, thank you, Rana Singh. I will add something. The solar cells, behind the development of new solar cells are the materials. So if the emerging technologies use different new materials to enhance the performance as well as reduce the material cost, production cost, like this. These perovskite solar cells come as a result of that. Okay, thank you, Rana Singh. Okay, let's move into the next presentation. Its title is Evaluation of Performance of Modified Graphene-based Material in Latex. In simple, it is a study on the latex films. Okay, our next presenter is Dirini. It's over to you.
This research title under Evaluation of Performance of Exfoliated Graphite-Based Materials in Latex Films was conducted with my colleague Udita Gamage under the supervision of Dr. NMVK Lienage, and I am Ashni Dilena from Department of Material Science and Engineering. To give a brief introduction on the topic, natural rubber is a widely used natural material in industrial applications, And especially when it comes to natural rubber latex films, it has a wide range of applications such as glove manufacturing, catheters, rubber bands, and swim caps, and etc. In order to improve properties of the rubber compound, additives are introduced into it, and this will also result in a reduction of cost. And as at now, silica is one of the most used fillers in natural rubber thin film manufacturing, and it is a known fact that silica improves mechanical properties such as tear and tensile strength of rubber matrix. But the issue in incorporating silica into rubber matrix is that silica particles are surrounded by hydrophilic sinyl groups, which are less compatible with natural rubber molecules, which are hydrophobic in nature. Therefore, silica is not easy to be used as reinforcing filler for natural rubber latex films without any surface modification or assistance of any other dispersing agent. In order to find a solution for the issue described in previous slide, we set up three objectives. First, to synthesize few layer graphite using mechanically assisted exfoliation technique, and then to develop natural rubber latex-based composites reinforced with silica modified using few layer graphite, and then finally to evaluate performance of the developed natural rubber latex-based composites. Even though there are a number of techniques being practiced in both industry and in research field to exfoliate graphite, we wanted to look for a more economical and less complicated method which can be easily being practiced in the industry. As a result of our literature review, we found out that ball milling is one of the most economical methods that can be used in this matter. And also we came across an attempt where melamine has been used as a grinding agent in dry ball milling assisted exfoliation technique. After further considerations, we decided to use Thamol NN19104 as the exfoliating agent in our process. So Thamol is a sodium salt of naphthalene sulfonic acid, which is already being used as a dispersing agent in the natural rubber latex film manufacturing. This fact already guaranteed us that our final exfoliated graphite will be easily compatible with the natural rubber latex. In the experimental procedure, our first step was to exfoliate graphite and characterize the exfoliated graphite. First, we had to decide on process parameters such as rotational speed of the ball mill, mass ratio between graphite and Thamol, and then are we going to use dry or wet condition for the ball milling. After several tries, we selected the best perform method and prepared a bulk sample from the selected method to be used in latex film preparation. Step first, to prepare aqueous dispersions of silica and exfoliated graphite, which was done using an ultrasonication mixing method. Then the final step was to prepare natural rubber latex films and characterize them. In order to do that, first we had to plan on preparing natural rubber latex compounding formulas, and then we prepared natural rubber latex dispersions with additives, and the prepared dispersions were then poured into molds, and next step was to dry and cure the natural rubber latex thin films, and finally they were characterized and the results were evaluated. In preparing aqueous dispersions of silica and exfoliated graphite, we tried out three different mass ratios as of 0.5%, 2%, and 3.5%, and also we prepared a dispersion with just graphite and silica to understand whether the exfoliating of graphite has been effective. By using these 5 dispersions, we prepared 5 different latex films to be characterized and evaluated. So you all can see in these compounding formulas, we used all the other additives at the same mass ratios, while the silica and graphite dispersions had different percentages of exfoliated graphite and graphite. Several different characterization techniques were used to characterize the natural rubber latex vulcanizates. First was optical microscopy, then scanning electron microscopy, and the swelling test was done. This is a conventional testing method used in rubber-related processes. Using this testing method, we can calculate swelling ratio and rubber filler interaction, get the cross-link density of rubber vulcanizates, as well as the interaction between rubber and the fillers added. Next, the tear strength test was done under STM D624 standard, and then the tensile strength test was conducted under STM D41206 standard. This optical microscopy images shows how the displacing ability of graphite has been improved by exfoliating them using thermal. And the SCM images of pure graphite and the exfoliated graphite clearly shows how our exfoliating process has been impact on the graphite sample. The right-hand side SCM image shows how the thick layers of pure graphite has been reduced into thin layers of pure graphite by the exfoliation technique. Here we have plotted the calculation results of crystalline density and rubber clay interaction using the swelling test. Crystalline density of rubber vulcanizate has been increased with the increased amount of exfoliated graphite being used, which directly affects the mechanical properties of the final rubber vulcanizates. When it comes to rubber filler interaction, usually if the rubber filler interaction indicator is higher than 1, it is to be said that the rubber filler interaction is lower. So when we look at the chart, we can see that if we use the same amount of exfoliated graphite and same amount of graphite in rubber latex vulcanizate, we can see that rubber filler interaction has been increased if the graphite is being exfoliated. And it can be identified that there is a limit to the amount of exfoliated graphite that can be used in the rubber matrix as after 0.2% of exfoliated graphite being used, it can be seen that the rubber fill interaction has been reduced. Analyzing the test results of tear strength test for rubber vulcanizates. The increased amount of exfoliated graphite, the tear strength of the final rubber vulcanizates will be gradually increased. Similar results could be seen in the tensile strength test results as well. After analyzing all the test results and evaluations, we can conclude that thermolenin 9104 has the ability to act as an exfoliating agent in dry ball milling assisted graphite exfoliation. And also, improved dispersion quality of silica in the rubber matrix can be achieved using exfoliated graphite. Nearly 100% increment in the tear strength of natural rubber latex films can be achieved by using exfoliated graphite compared to the control with only precipitated silica as the filler. We also have few suggestions for future work related to this research topic. Evaluating all the results and the experience gained throughout the research, it can be suggested that higher results can be obtained by using a planetary ball mill instead of conventional ball mill. In conventional ball mill, the rotational axis is horizontal, but in planetary ball mill, the rotational axis is vertical. Using smaller grinding media, we could have achieved a less number of layers of final exfoliated graphite. And also the preparation technique of silica and exfoliated graphite aqueous distillation can be optimized, which will directly affect the final results. And finally, the curing process of the rubber latex films can also be optimized. When we introduce graphite into natural rubber latex matrix, it is a known fact that the thermal conductivity properties of the final rubber vulcanizate will be different. Therefore, it is possible to use this optimization process as further detailed research. Last, we would like to acknowledge the great assistance given by the academic and the technical staff of the Department of Materials Science and Engineering, University of Moratuwa, throughout the time period of the research.
Okay, thank you, Dilini. Now it's time for questions. Dilina, yeah.
Yes, madam, I'm here.
Yeah. Now, it is time for the questions. While others are asking questions, I will ask small question. Is this experimental or theoretical research?
This is experimental, madam.
Experimental one.
Yes.
Okay, good. Then have you prepared the latex film?
Yes, madam. Like we had the chance to attend to the university and do this research at our laboratory.
Okay.
So
Okay.
we had the films and did all the testings.
I saw in your tensile results the highest tensile was given with some sample name as EC G, no? EG 0.35. Can you move that tensile property variation? Okay. As the recording you may not, but what is the optimized condition, that you optimize amount of graphene for the highest performance?
That's
properties?
0.35 PHR.
0.35 PHR. Okay. Do you explain any reasons for why that particular amount shows the best performance?
As our as assumptions, madam, when we exfoliated graphite, it acts as a coupling agent in between silica particles and the rubber particles. So the interaction between rubber particles and the silica particles has been input. So that results in the increase in tensile strength.
Yeah, that I asked that 0.35 gives the best
Maximum
performance.
value. Yes, that is the maximum amount we used. Yes.
That is the maximum amount you use.
Yes.
0.35. Okay. Okay. Any other questions? As no questions, shall we move to the third presentation? The title of the third presentation is Modeling of Micro-Size Ultrasonic Generator and Receiver Characteristics of Lead Zirconate, Titanate and Polyvinyl Chloride using finite element analysis. Actually, this project is on piezoelectric materials. Our third presenter is Pathipan.
Hello everyone, I'm Kazan Keevan from Department of Material Science and Engineering, University of Moratuwa. This research was conducted along with my colleague Parthiban under the supervision of Professor S.U. Adhikari. Without any further delay, let's move to the presentation. My research topic is modeling and simulation of micro-size ultrasonic characteristic of lead zirconate titanate and polyvinyl fluoride. This is a brief introduction of our research. When we took the ultrasonic wave, they are longitudinal mechanical waves that have frequency greater than 20 kHz, which means beyond the human hearing ranges. By considering the frequency of ultrasonic wave, we can classify them into two categories. First one is a low frequency category that has the frequency in between 20 to 1000 kHz. And the second one is a high frequency category that have the frequency above 1 MHz. An ultrasonic transducer itself is a device that can generate and receive ultrasonic vibration. Here we have chosen our active element as a piezoelectric material, which can be convert the electrical energy to the mechanical energy, and it can be occur in vice versa as well. When we move to the objective, the first objective is to model the ultrasonic generator and the receiver using CAMSOL multiphysics software. And the second one is to observe ultrasonic characteristic of lead zirconate titanate and polyvinyl fluoride as a piezoelectric material with the use of finite element analysis. And finally, to obtain the ultrasonic characteristic for microsonic ultrasonic devices. Let's move to the material selection. Here we have choose our material based on several factors such as electromechanical coupling coefficients, acoustic impedance, and etc. The first material we have chosen was piezo ceramics. Particularly, we have choose P35H, which is a metallic oxide that has perovskite crystal structure, which can offer high permittivity, high coupling factors, and piezoelectric constant. Mostly, the P35H is used in fine moment control and high sensitivity receiver application. On the other hand, the P35H is difficult to fabricate the complex shapes and has restricted temperature ranges in its applications. And moreover, it's not environment friendly. The second material we have chosen is PVDF. PVDF is a piece of polymer. It have high piezoelectric voltage coefficients, and also it's very easy to fabricate the complex shapes. However, the PVDF have suffer with its mechanical properties due to its various type of radiation such as vacuum, UV, X-ray, gamma rays and charged particles. And also it can be suffer with extreme temperature fluctuations. This table compares some of the essential properties of PVDF and PZT5H. The model layout. The design methodology for obtaining the best suitable piezoelectric material for ultrasonic sensing and generating application. Here we used disk type model configuration for our further analysis. Let's move to the mathematical calculations. The induced voltage was determined use of piezoelectric constitutive equations with some set of assumptions. The assumptions are used to reduce the complexity in the mathematical calculation derivation steps. In order to determine most appropriate applicable voltage, the concept of dielectric breakdown was used across the electrodes of generator material. The next step was finite element analysis, and it were conducted through the CAMSOL multiphysics software. By considering the accuracy, 3D model was selected instead of 2D asymmetric in microscale. The ultrasonic characteristic of PVDF and P35H were analyzed through the 4 different cases. For instance, using P35H as a generator material with the PVDF and P35H as a 2 separate ultrasonic receiver material. And the designated dimension of receiver, medium and the generator are given in the table. The air was taken as a medium and the mesh type for the simulation was selected by considering the accuracy of output and also the computation time. Let's move to the resultant discussion. The resonant frequency in which the piezoelectric material effectively converts the energy from one form to another with a low energy losses, and the simulation was carried out in the resonant frequency of the receiver materials. Following that, determination of resonant frequency of the receiver while PZT5H as a generator. Here 10 voltage was applied to the generator at 1 MHz to 20 MHz frequency to obtain the resonant frequency of the receiver. When P35H was selected as a receiver, the highest displacement was found at the frequency of 13 MHz. And also, when the PVDF was selected as a receiver, the highest displacement was found at the frequency of 10 MHz. The next is to determine the resonant frequency of the ultrasonic receiver while PVDF as a generator material. Here in receiver material, the highest displacement was obtained at 5 MHz. Without let you to struggle with a deep analysis by looking each and every case separately, I have summarized all the output result in one table for your easy understanding. From our result, our discussion, the table 1 shows result obtained from the finite element simulations. It shows whatever the material used as a generator, PVDF shows the highest output electric potential compared to the PZT5H as a receiver material. The table 2 shows the value of induced electrical potential and the displacement from the mathematical calculation. Similar to the finite element simulation results, the mathematical calculation results also show that regardless of generator material, the highest output electrical potential encountered when PVDF used as a receiver material. And finally, the conclusion was derived according to the result which we got from the mathematical calculations and finite element simulation results. The PZT5H material is better for ultrasonic generator application because it's produced high induced electrical potential value in receiver material. And also PVDF is better for ultrasonic sensing application because it's produced high induced electrical potential value as a receiver, while whatever the material used as a generator material. As you all know, the ultrasonic transducer have been used throughout many applications and industries. By utilizing the proper material in ultrasonic transducers, we can efficiently use and conserve the energy for future. Thank you.
Okay, thank you for your interesting presentation. Now others can ask questions. Okay, so you can ask.
Oh, okay. Sasanki, then what do you mean by micro-size ultrasonic characteristic?
Basically, we design our ultrasonic transducer in micro size scale. So with the evaluation of technology, we are reducing the sensor size. So that will easy to install this transducer in any other application. So that's why we are mentioning micro size ultrasonic. We are developing the ultrasonic all the.
Okay, so right. So now normal sensors are millimeter size. Now you are going to the level of micrometer size, right?
Yes.
So did you find any difference in the characteristics between because of the size difference?
Due to the size difference, compared to the millimeter scale, micro scale have very low output. But we can amplify those signals and get our usual ones.
So you found that output is not up to that level.
Yeah. But we can rectify that issue with amplification technology.
Mm-hmm. So what is the purpose of reducing the size of the sensor here?
As I already mentioned here, with the evaluation of technology, we have to reduce the size. So that's the trend of the technology.
No, that is okay. Now, right, bringing the size or minimizing the size of that is okay. But now you said by minimizing or reducing the size, you are saying that the efficiency has gone down, right? You said output is less.
Yeah.
Yeah. So then what is so? If the output or the efficiency is going down, so there is, in my view, right, you had explained, there is no point in reducing the size.
Yeah, when you compare the efficiency, the output is going to reduce too. But in overall performance of, when we consider the overall instrumentations, reducing the size is better effective than these low output.
Okay, right.
Okay, thank you very much for your question. And Tasankitan, can you mention any applications of this kind of transducers?
Yeah, we can use this transducer in many applications. Specifically, we have focused to the to implement this transducer in blood pressure measurement equipment. And rather than that, we have used in several automobile industry and distance measurements and several applications are there. We can implement this micro-size sensor there.
The depend on it is the properties.
Yes, yes.
Okay. Okay, thank you, Tasan Kitan, for your, thank you for your presentation.
Thank you.
Okay. Then our fourth presentation is on simulation study on the insulation properties of cotton fiber LDPE composite. The basically study on composite materials. In here the presenter, our fourth presenter is Manivel Vadu.
Supervised by Mr. S.V. Udayakumar.
We'll move on to the introduction then. First, as engineers, we identified a real life problem which we can give a sustainable solution. Actually, we know Sri Lanka is well known for its textile products. Textile industry represents 43% of country's total exports. Out of them, cotton is the most widely used fabric and the waste production falls 20% to 30% from the total fabric used. Just imagine the waste production falls under this production of this textile. When comparing with the other natural fibers, cotton takes a considerable time period to grow, as well as the water footprint of cotton tree also considerably higher. That means the amount of water consumed by cotton tree when compared to others is relatively high. So we identify the hidden value behind this cotton tree, and as researchers we thought of a new method to reuse these cotton waste. When we talk about plastics, since 19th century people use plastics. There are different types of plastics such as polyethylene, polyvinyl chloride means PVC, polystyrene, etc. These plastics take more than 100 years to decay. And the worst scenario is most of this plastic waste enters our environment, polluting the oceans and harming the ecosystem. In Sri Lanka also you could experience this whenever you visit a beach. You could see here and there PET bottles and plastic waste. So as materials engineers, we had an aim to think of a new method which we can reuse them, both plastics and cotton fiber. So we thought to develop a computational model of a composite made from cotton fibers and low density polyethylene, means LDPE. So as our aim is to develop a computational model using cotton fibers and waste plastics, let me introduce you what is meant by a computational model. A computational model means a mathematical model which is used to simulate and study complex systems, adjusting the parameters of the system and studying the differences in the outcome of the experiment. So here you could see an outcome which is generated by a computational model. COMSOL Multiphysics 5.5 was used to do the simulation. It consists of various modules and composite material module was used to do the simulation. The same software can be used to simulate electromagnetics, structural mechanics, heat transfer, chemical phenomena, and many more. When it comes to computational modeling with COMSOL, first of all, we developed a model for a specific geometry which we can change the percentage of cotton and LDPE as desired. So here in this figure, you could see that there are three layers, and in these three layers, we could change a percentage of cotton and LDPE percentage. And while changing the percentages, we kept the bottom surface temperature at room temperature and the top surface temperature at a higher temperature like 373 Kelvin. As I described in the previous slide, we have kept two temperature probes which are at the top and the bottom surface. The bottom surface was kept in a higher temperature while the top surface was kept in the room temperature, and with the time the temperature change can be generated using the COMSOL solver. So here in this figure you could see how the temperature change has been occurred. So while changing the percentage of cotton and LDPE, we studied the variation of top surface temperature. You could see that the bottom surface, the surface which we kept in a higher temperature, has a steep temperature gradient which is denoted by red color in this figure. And when it reaches to the other end, the temperature gradient reduces, which is shown by blue color. So we studied the temperature gradients by changing the percentages of LDPE and cotton. Then, when considering the results of the boundary probe, which is kept at the room temperature, you could see that in this graph, when the time increases, the temperature has been increased. So we generated these kind of graphs for each percentage of cotton and LDPE, and then we understood that when the cotton percentage increases, the top surface temperature, the time which has taken the top surface, when considering the results of the boundary probe which is kept in the top surface, we could see that with the time the top surface temperature has been increased. So we generated this kind of graphs for each and every percentage of cotton and LDPE, and finally we understood that when the cotton percentage increases, the time taken to increase the top surface temperature is also getting increased. When we move on to our results and conclusions, we got a negative correlation between the temperature difference of the top probe versus the cotton volume, which means the temperature difference of the top probe is inversely proportional with the cotton volume. Moreover, the temperature difference of the top probe is getting reduced while the cotton volume is being increased. So that means when we are increasing the cotton fiber volume fraction of the composite, the thermal insulation properties of the composite also increases. So finally, we determined that cotton fibers can be used effectively as a composite material with LDPE to use as an insulating material. With that explanation, that concludes our research presentation. Thank you all.
Okay, thank you, Magalia, for your presentation. Now we can ask questions. Okay, Mugalaya, what are the input parameters of this simulation study?
Actually, madam, we used input parameters means that temperature probes. We set the temperature probes of the two layers, and that means the upper side and the lower side, and also we used the material data of LDP and cotton as input parameters as well.
Then have you studied the effect of these input parameters, or
input parameters means now we kept the material properties were kept constant, and the temperature and the phase angle was the parameters.
Okay. Then can you comment on the effect of these temperatures? The insulation properties.
Sorry, madam, not the temperature, the cotton and LDP percentage. The temperature was also kept constant.
Constant. Okay. Then can you explain the insulation properties of with the percentage of cotton fiber, change in the cotton fiber percentage?
Yeah, we found that when we increasing the cotton percentages, the thermal insulation property is also getting improved. That means the top surface temperature is somewhat lower. It's getting lower when we are increasing the cotton percentage. So that means finally the insulation properties are getting increased when we increase the improved when we increase the cotton percentage.
Okay, then up to what limit we can incorporate these cotton fibers? The maximum amount? Have you studied it or not?
Yeah, we just in this study we only studied up to 70%, but we didn't move on to rather than 70% of cotton.
What about the effect of this amount to other properties? Have you measured other properties, other mechanical properties?
Yeah, the thing is we didn't measure the mechanical properties because in COMSOL we need another. It's a separate part when we if you want to measure the mechanical properties. So with those restrictions, we could only measure the insulation properties, madam, with this module.
Okay. Thank you. Any other questions? Okay, as no questions, once again, thank you, Magalia. Then the last presentation is our last presentation is on modeling the mechanical behavior of microcrystalline cellulose-based polymer composite materials. It's also another composite study on composite materials. Our last presenter as given to me, Sukrita.
Good morning, all of you. I am presenting our final year project to you, which is the modeling the mechanical properties of microcrystalline based polymer composite. Nowadays, go to introduction. Nowadays, composite materials are preferred than homogeneous material due to the better properties. Polypropylene material has been widely used for engineering application, and cellulose-based composite is often used for engineering applications than fiber composite. And cellulose have a better mechanical properties than fibers. From this slide onwards, you can see some industrial application of cellulose-based composite. First and major priority is automobile industry. Because composite have a high strength and low weight, which is leads to increasing the practice of composite in automobile industry. Continue the application of composite. Marine industry also have major application of composite material because of it is high stiffness and low weight. Cellulose act as a higher reinforcement material. Go to next slide. When consider the sports sector, we all knew that sport goods are made by fiber. In advance, composite materials take an important place in manufacturing because of high quality, high weight, strength and comfort. Other important sector is biomedical industry. Composite materials use most advanced technology and produce nano-size equipment in medical world. Due to the good electrical properties of cellulose-based composite, it was used the electrical industry by using the different composition. But our project purpose is overcome the gap between the theoretical outcome and practical scenario. Because even though we have a lot of advantages on composite material, we can't find the actual composition for required properties. So our initial solution for this problem is mathematical model to predict the mechanical properties. This research done by using the basic rule of mixture composition of equations. Go to next slide. Normally, rule of mixture equation denoted by this equation. Here, all the parameters are donated in respective parameters. Sigma F is the strength of fiber, sigma M is the strength of matrix, Vf is the volume fraction of fiber, Vm is the volume fraction of matrix. Go to next slide. In this slide, show the mathematical derivation. Composite material were derived from basic rule called rule of mixture. Model was developed with a basic assumption on composite. Here, fiber imperfection was considered into the model that was affected more. So, agglomeration, fiber length, and orientation factors was added to this model. And we take the simplified assumption such as the continuous unidirectional fibers uniformly distribute throughout the matrix, equal strength in all fibers, defects-free aligned fibers and matrix, in addition to perfect bonding. These are the assumptions we take. Additionally, load efficiency factor was at both part, fiber and matrix. After that, geometrical factor also add to the model due to the cellulose is rod-like shape. Geometrical factor depend on the diameter of the cellulose and finally we use this model for analyze for tensile strength. This graph clearly shows the theoretical versus experimental trend. Experimental value was higher than theoretical values. When considering the gradient of the two graphs, correction factor 1.5 to be had to the theoretical model to equate the experimental value. And also consider the factor that have been affected the gradient and constant factor will be added to the particular factor. Go to next slide. This slide is simplify the elastic modulus models. Elastic model also have some modification as tensile model without geometrical concern. So the model will be affected only the cellulose part. For the last module comparison, initial experimental values were less than theoretical values, then overcome the theoretical values. Here, correction factor used in the 1.25 to equate the gradients. Then go to next slide. These models amplify the impact strength of the composite. Impact strength majorly affected by length of the cellulose part, so that model will be arranged by this format. Parameters are given flow. U C is the strain energy of the composite. Vx the volume fraction of fiber, Vm is the strain energy of matrix, sigma f is a fraction of single fiber, y is the length of fiber, d only period to fiber fraction in composite, length of the fiber L, Lc is the critical fiber length. These are the parameter indicator composites, impact strength of the composites. Go to next slide. Impact strength experimental values were less than the theoretical values as expected. Almost 10 is aligned with the experimental values, also correction factor also 0.92. Finally, these are the final models are derived through the experimental comparisons with the theoretical analysis. From that, we can predict the mechanical properties of composite by using the composition. Finally, we conclude that the mathematical model almost aligned with the experimental trend and correction factors were added to the better results. Defect factors of composite also suggest to further research. Thank you.
Okay, thank you, Sukirta, for your nice presentation. And now it's time for questions.
Sukirta, can you hear me?
Yes.
Hi, Sukirta. Basically, with respect to your presentation, what is the practically, I mean, how do you see that it is useful for the industrial people? I mean, how it is relevant? What is the bridge that you are going to build?
Normally, we need to considering the material designing. We need to the how much of the reinforcement and the fiber and matrix. We need to how what amount need to the material design considering. So we consider that how many amount of the fibers we need to and how many amounts need to the matrix. That's a fiber means such as the microcrystalline cellulose and matrix means the polymer material.
When we design that composites product, we considering the material designing using this equation. We calculate the mechanical strength and plastic modulus and impact strength.
Okay. Do you have any plan to do it experimentally in the future? I mean, now this is completely modeling work, right?
Yes, but we did that theoretical and practical value. After that, we developed that model, but we didn't know the industrial applications.
Okay. Okay. Thank you.
Okay, thank you. Thank you. And in this model, actually really interesting. You show in your graph, I have seen that there is the trend matching between the experimental and theoretical values. Where did you get that experimental values?
We did that measuring that properties, mechanical properties.
That means you have done the experimental part as well. Or
yes.
Did you obtain those values from the literature?
No. We did that theoretical, experimentally.
Okay, good. That means you have done the both part.
Yes.
Okay.
Basic equation we got that from Little service. After that, we developed that equation and we put into that value and we find the theoretical value. Then we did that experimentally. We got that value.
Okay. Actually, you already validate to some extent the model, no?
Yes.
Okay. Thank you, Sukirta.
Thank you for this opportunity. Thank you.
Any other questions? Okay, as no questions, that is the final presentation. I'd like to thank thank to all our presenters for their presentations and discussion. As well as I'd like to thank all the attendees. And I appreciate this presenters' work in this the different discipline actually because of the pandemic situation. They had to move into that computational skills. They had to use that skills. Actually, I really appreciate your hard work during this time and ending your final year project in this successful manner. Okay. Thank you all. Now I will hand over this session to the organizing committee.
Okay, thank you, Dr. Aisha, for sharing the technical session 2. And actually, we are in the verge of closing the our 4th symposium. To be clarify on that, I mean, this is the first time we are doing our normal symposium in online mode. There are certain challenges that we do when we conducting online sessions since the dependency of several hardware and several other services. But anyway, I think with today's program, I think starting from the inaugural session until now, as the industrial personnel and our students, undergraduate students and semester 1 students, you might have obtained a certain glance what is the Department of Material Science and Engineering is all about and what are the things that we do. And also from the chief guest talk, actually it was clearly mentioned what are the other ends that we can travel. And I appreciate actually to all these speakers and all the undergraduate students who had actually conducted, presented their technical presentations in this particular forum. And I also thank some our other undergraduate students who has given to me some technical assistance and other assistance in arranging this kind of symposium in much more challenges time. So I hopefully think on next year we will have a physical face-to-face sessions, and let's hope that is possible in coming sessions. So thank you very much for your time, and we will meet again in the next year's symposium. Thank you very much again.